8 planets move through the dark around our sun. 4 are small and rocky, pressed close to the warmth. 4 are vast and gassed and cold, swinging wide arcs in the outer system. Mercury, Venus, Earth, Mars, each one under 1,000 miles across, each one a ball of iron and silicate with a skin of crust. Then a gap of stone and ice, and then the giants, Jupiter with its red storm, Saturn wrapped in rings, Uranus and Neptune tilting through the long outer dark. 8 worlds, a whole solar system arranged across 500,000,000,000 miles of space. And in all of it, in the entire long inventory of everything the sun holds, there is not a single planet between the size of Earth and the size of Neptune. That gap is not a coincidence. It is, as far as we can tell, the strangest thing about our home. Everywhere else in the galaxy, that gap is full. The planets that fill it have a name. They are called super-Earths, and they are the most common kind of world in the Milky Way, a type of planet so ordinary, so routine, so relentlessly prevalent around other stars, that the solar system we live in appears to be the exception, not the example. They are worlds with masses ranging from just above our own up to about 10 times Earth's. Rocky bodies larger than anything we have ever stood on, heavier than anything in the familiar four, and absent from our sky entirely. To look at the 8 planets in order and know that the most abundant planetary class in the galaxy fits nowhere in the sequence, sits in the blank space between the 4th world and the 5th, is to understand, slowly and with some weight, that what we grew up calling a solar system is not quite what a solar system usually looks like. The nearest star to the sun is a red dwarf, smaller and cooler than our own, and it likely hosts a world in this size range. So does the second nearest, and the third, and most of the ones after that. They recede into the dark in every direction, a population of worlds so dense in the galaxy that if the sky could somehow be made transparent to show what orbits each point of light, the darkness above would resolve into a field of rocky, heavy planets, too numerous to count, orbiting close to their stars in the quiet and the heat. Coming to understand this took time. For most of human history, the word planet referred to exactly 8 things. 7 if you removed Pluto, 9 if you hadn't yet, and all planetary science was solar system science, because there were no other planets to study. The assumption, usually unspoken, was that what we had was roughly what there was: small rocky worlds close in, large gassed worlds far out, a neat arrangement that seemed, in its familiarity, like a template. The solar system was not studied as one example drawn from a larger population. It was studied as the population itself. The Kepler Space Telescope changed this. Launched in 2009, it watched a single patch of sky for years, measuring the brightness of more than 100,000 stars simultaneously and recording the tiny dips in starlight that occur when a planet crosses in front of its host star. Each dip was small. A planet the size of Earth crossing a sun-like star reduces its light by less than 1/100th of 1%, but the telescope was precise enough to catch them, and it caught them in enormous numbers. By the time the full statistical picture emerged, the most common result was not a Jupiter, it was not a Neptune. It was something in between Earth and Neptune, massing between 1 and 10 times what our planet weighs, orbiting its host star in days or weeks rather than years. Super-Earths and their close atmospheric cousins, mini-Neptunes, everywhere. The distribution was plotted. Thousands of detected planets, their radii measured and arranged on a graph, each one a point in a long sequence, running from the smallest to the largest. And in that graph, in the accumulation of all that data, In the patient arithmetic of light curves and orbital periods and stellar radii, something appeared that was not expected. A gap. Not a gap between Earth-sized worlds and Neptune-sized worlds, though that gap existed too. A smaller gap sitting inside the broad range of sub-Neptune planets between 1.5 and 2 times Earth's radius. On the graph, planets clustered on either side of this narrow band, but within it they were rare. A ridge, then a valley, then a ridge again. The empty space between the two populations was not wide, but it was real, and it was deep enough to be statistically unmistakable. It appeared in 2017 in work done by the astronomer Benjamin Fulton using refined Kepler data, and it became known as the radius gap. The radius gap did not appear by chance. It appears in the data because two kinds of worlds that conform in the same mass range end up in different places on the size scale, sorted by whether they manage to hold onto their original atmospheres. On one side of the valley, super-Earths, rocky and dense, their original hydrogen and helium long since stripped away. On the other side, mini-Neptunes, worlds of similar mass, but wrapped in thick envelopes of light gas that puff their radii outward, making them larger than their masses alone would suggest. The same weight, two very different worlds. And between them almost nothing, because the forces that strip atmospheres are efficient, and the gap between stripped and unstripped tends to be sharp. The stripping happens early. Around a young star, the radiation pouring from the stellar surface is not just visible light. There is extreme ultraviolet, and there are X-rays, and in the first few 100 million years of a star's life, these high-energy forms of radiation arrive at the planet's upper atmosphere with enough energy to heat the gas above the planet's escape velocity. Hydrogen, being the lightest element, is the most vulnerable. It rises, reaches the exosphere, and drifts away. On a rocky planet with a mass close to Earth's, this process, called photoevaporation, can remove an entire hydrogen atmosphere within a few 100 million years. On a more massive planet, one with higher gravity, or one that formed farther from its star and received less radiation, the same atmosphere might persist. The outcome depends on mass, on distance, on the brightness of the star's early life. The gap in the radius distribution is the signature of that sorting process, written in the sizes of thousands of worlds, orbiting thousands of stars. There is a second mechanism that likely contributes. Deep inside a young rocky planet, heat left over from the violence of formation slowly seeps outward through the rock. If enough of this heat reaches the base of a primordial atmosphere, it can drive an outward flow of gas, lifting it off the planet over millions of years, even in the absence of stellar radiation. This is called core-powered mass loss, and it operates on longer timescales than photoevaporation, millions to tens of millions of years, rather than hundreds of millions, but it pushes the same direction. It clears atmospheres. It widens the gap. The two mechanisms are not in competition. They work together to enforce the sorting, and the valley in the radius distribution deepens as a result. Stand at the edge of that gap and look across it. On the near side, a super-Earth, dry, dense, its surface of iron-gray rock unmarked by any ocean, its atmosphere thin or absent, its mass enough to hold a person's feet more firmly to the ground than anything our own solar system offers, but not enough to have gripped the hydrogen that once lay above it. On the far side, a mini-Neptune, same mass or close to it, but wrapped in a soft haze of hydrogen and helium that extends its visible edge a third or half again as far from its center as the rocky worlds, its upper atmosphere warm and diffuse and pale, its density lower than water. Two planets that weigh the same, sitting side by side in the dark, as unlike each other as a stone and a cloud. The distinction between them is not merely a matter of appearance, it is a distinction of origin, of location, of how much radiation fell on them when they were young, of whether their initial hydrogen envelopes survived the first billion years. A mini Neptune that loses its atmosphere over geological time, stripped by radiation or by the slow outward press of residual heat, slides across the gap and becomes a super Earth. The gap is not just a feature of today's planet population. It is the record of a transformation that happened across billions of years to billions of worlds, preserved now as a quiet absence in a graph. The graph itself has a quality that stays with those who study it. On one axis, the radii of thousands of detected exoplanets, measured in multiples of Earth's own radius. On the other axis, the frequency with which each size appears. The distribution rises, peaks, dips, rises again, and falls. The dip, the valley, the radius gap is narrow in absolute terms, only half an Earth radius wide, a sliver of the full range. But it is conspicuous in a way that simple randomness would never produce. It is a signal. It is the galaxy writing a record of atmospheric physics in the sizes of its worlds, and the record is legible to anyone who looks at enough planets and plots what they find. Not every star offers the same view into this gap. The Kepler survey was weighted towards sun-like stars, stars of roughly the same size, temperature, and brightness as our own sun, because these were the most straightforward to interpret. Around sun-like stars, the radius gap sits clearly between 1.5 and 2 times Earth's radius. Around smaller, cooler stars, the gap may shift slightly because the radiation environment is different, and the same mechanisms play out at different rates and different distances. The underlying physics is the same. The specific numbers change with the star. Around M-dwarf stars, the small, cool red stars that make up roughly 3/4 of all stars in the Milky Way, the picture becomes particularly dense. These stars are dim, they are long-lived, they are common, and the statistical analysis of planets found around them suggests that nearly every one hosts at least one planet in the super-Earth or mini-Neptune size range. Not most M-dwarf stars. Not a majority of them, nearly all of them. The fraction is high enough that astronomers describe M-dwarfs as practically guaranteed to have at least one small, close-orbiting rocky world. The sky is full of them. Every third or fourth star visible on a clear night is an M-dwarf, and nearly every one of those faint red lights, too dim to see without a telescope, is orbited by something in the mass range our solar system entirely skipped. The numbers are worth holding quietly without rushing to measure their edges. Somewhere between 30 and 50% of sun-like stars in the Milky Way host at least one super-Earth or mini-Neptune in a close orbit. Around M-dwarf stars, the fraction is higher still, perhaps 70 or 80%, perhaps more. The Milky Way contains a few 100 billion stars. Most of them are M-dwarfs. The arithmetic, done slowly and without emphasis, points toward a number of super-Earths in the galaxy that is not hundreds, not thousands, not millions, but hundreds of billions. These worlds are not exotic. They are the baseline. They are what planets tend to be. The solar system is not the baseline. The solar system is an outlier in at least this one respect. The question of why it lacks a super-Earth has no settled answer, and this is not the place to pursue it fully. But the absence itself is real, and it is significant, and it shapes the experience of living here in a way that becomes visible only from the outside. We evolved on a world that orbits in the gap. Our only planetary neighbors in the rocky size range are smaller than us, or barely our size. The next class of planet beyond Mars is Jupiter, not a super Earth, not a mini Neptune, but a gas giant, more than 100 times Earth's mass, an entirely different kind of world. The step between Mars and Jupiter in mass skips over the most populated region of planetary space entirely. Looking at the 8 planets in order, knowing what the galaxy's broader population looks like, gives the sequence a quality of quiet peculiarity. The rocky four are all small. The gas four are all enormous. The middle is empty. That middle, the space between a few Earth masses and the lower edge of Neptune's mass, is where most of the galaxy's planets live, and it is where the solar system has nothing. One way to feel the size of a super-Earth: Earth's diameter is about 8,000 miles. A super-Earth of twice Earth's mass would have a diameter somewhere between 9 and 11,000 miles, depending on its composition, wider than Earth, but not enormously so, not in the way that Jupiter's diameter of roughly 90,000 miles is enormous. Standing on the surface of such a world, the horizon would be a little farther away than it is on Earth. The sky would feel the same width, but the weight of the air would be greater, the atmosphere compressed more firmly by stronger gravity, and the weight of a body would be greater too, a person pressed more insistently into the ground. The planet would feel heavier in a literal sense. The rock under the feet would feel more final. A super-Earth of 5 times Earth's mass would be different in kind, not merely degree. Its surface gravity could be more than twice our own. The weight of a body would double. Breathing would take more effort. The bones would be loaded in ways evolution never prepared them for. The sky would be deeper, not taller, but denser. The atmosphere stacked in thicker, heavier layers. The pressure at the surface several times what it is at sea level here. The planet would be large enough that the curvature of the ground would be slightly less apparent than on Earth. The world would feel, if anything, flatter, though the gravity would feel much more present, a constant insistence downward, heavier than anything on the surface of any world humans have ever touched. These are not hypothetical worlds. They exist. They have been found, measured, characterized, cataloged. Some are close, in astronomical terms, within a few dozen light years, within what would be, on a cosmic scale, an almost trivially short distance, though still immeasurably far by any human standard. They sit in their orbits, some of them in the habitable zones of their stars, some close in and hot, some in longer periods and cooler. They have names drawn from their stellar host and a letter designation, a catalog entry, a data point, a brightness curve and a mass estimate and a radius measurement. They are real. What they do not have, as far as is known, is anyone on their surface looking back. The question of what those surfaces look like, bare rock under high gravity, or oceans held at strange pressures, or magma still cooling from the heat of formation, is not simple to answer from the data available. A transit measurement gives a radius. A radial velocity measurement gives a mass. Divide mass by volume and get a bulk density, and from bulk density one can make inferences. If a planet is dense enough, it is probably rocky. If it is less dense, it likely holds a significant fraction of light gas or water. But the inference stops there. The interior structure, the surface conditions, the atmospheric composition, all of these require more, require spectra, require time on large telescopes, require patience. The planets are known to exist. What they are like in any detailed sense remains, for most of them, open. What the data does give clearly is the prevalence, the frequency, The ordinariness of super-Earths as a planetary class, repeated across the galaxy with a consistency that says, this is what happens. This is what planets tend to be when they form. This is the outcome that stellar physics and disk physics and the chemistry of condensing solids produces over and over again around star after star after star. The solar system, with its specific and somewhat peculiar arrangement, small rocks, giant gases, nothing in between, is not the model. It is one case among a vast and varied population of planetary systems, and it is a somewhat unusual case. The field of planet detection has moved fast enough that the concept of rarity has had to be revised repeatedly. First, planets outside the solar system were thought to be rare. Then they were found to be common. Then super-Earths were detected in small numbers, and tentative conclusions were drawn. Then the numbers grew. And then, with the full Kepler dataset processed and the statistical analyses complete, the conclusion was unavoidable. The most common kind of planet in the galaxy was not represented in the solar system at all. It was a class that had no analog in the only planetary system ever studied in detail, and it was sitting in the most heavily populated region of planetary parameter space, and it was everywhere. The radius gap sits in the data like a quiet mark. It says, there are two kinds of small planets sorted by their atmospheres. On one side, rock. On the other, rock wrapped in gas. And between them, a narrow empty band that is the record of a process of light from a young star falling on a young planet and lifting its atmosphere away grain by grain, molecule by molecule, over hundreds of millions of years. The gap is physics made visible in a statistical distribution. It is the fingerprint of photoevaporation pressed into the census of a galaxy's worlds. A planet on the rocky side of the gap has lost something. It had, in its early life, a hydrogen envelope, light and vast and puffy, drawn in from the surrounding disk during formation, gathered by the growing gravity of its core. For a time, perhaps for tens of millions of years, it was not a super-Earth but something closer to a mini Neptune, shrouded in gas, its surface inaccessible beneath a deep atmospheric column. Then the radiation came. The star, young and bright in the extreme ultraviolet and X-ray bands, poured energy into the upper atmosphere, and the hydrogen, heated past the escape velocity, began to flow upward and outward into space. The process was slow, measured in geological time, but it was steady, and eventually the envelope was gone, and what remained was the rock. That rock is what the surveys are finding, not the hydrogen envelope that has long since dispersed into the stellar wind and the interplanetary medium, thinned to nothing. The rock persists. It transits its star in its regular orbit and dims the starlight by a predictable fraction, and the telescope measures the dip and records the period, and the radius falls out of the calculation, and the world is catalogued. The hydrogen is not there to measure. It left a long time ago. The distinction between a super-Earth and a mini Neptune lies in part in the distance from the star. Close-in planets receive more radiation, lose their envelopes more easily, and sit on the rocky side of the radius gap. Farther-in planets or planets orbiting quieter, cooler stars may retain enough gas to stay on the mini Neptune side. The gap is not determined by mass alone. It is determined by mass and irradiation together, by how much the star gave and how much the planet could hold. A planet of two Earth masses orbiting very close to a bright star is probably a bare super-Earth. The same mass orbiting farther out or around a quieter star might still carry its hydrogen envelope. Mass and location in combination determine where a planet sits in the distribution. This nuance makes the radius gap more interesting, not less. It is not a binary division, it is a probabilistic sorting, and the boundary between the two populations is not perfectly sharp in every case. Some planets sit near the gap itself, uncertain in their classification, their measured radii placing them in the transition zone between the two populations. These are the most interesting objects for those who study the gap, because they are the ones closest to the boundary between two planetary fates. But for the broad population, for the thousands of planets that cluster on either side of the valley, the sorting is clear. Rocky worlds below 1.5 Earth radii, gas-wrapped mini-Neptunes above 2, and between them, a narrow band where few worlds reside because the physics that separates the two classes is efficient and the middle ground is unstable. The stars around which these worlds orbit are also, in the broad statistical view, mostly not like the Sun. The Sun is a G-type star, not rare, but not the most common. G-type stars make up about 7% of the stars in the Milky Way. K-type stars, slightly cooler and smaller, make up about 12%. Mem-type stars, the red dwarfs, cool and dim and long-lived, make up roughly 73%. Nearly 3 out of every 4 stars in the galaxy is an M-dwarf. And around M-dwarfs, the planet statistics are particularly dense with super-Earths. The reason is partly observational. M-dwarf stars are smaller, so a planet of a given size blocks a larger fraction of the star's light during transit, making detection easier. A super-Earth crossing a Sun-like star dims it by less than 1/100%. The same planet crossing an M-dwarf dims the star by a much larger fraction, perhaps 1/10% or more, a signal an order of magnitude stronger and easier to detect. The surveys are more sensitive to super-Earths around M-dwarfs. Some of the apparent preference of super-Earths for M-dwarfs may be a detection bias, but when the bias is corrected for, when the statistics are adjusted to account for the fact that the surveys see M-dwarf planets more easily, the conclusion holds. M-dwarf systems are genuinely dense with small rocky worlds. The closest M-dwarf stars to Earth, Proxima Centauri, Barnard's star, a handful of others within a few light years, appear to have planets in this size range. These are not distant examples, they are the nearest neighbors. The solar system sits inside a region of the galaxy where nearly every point of light is an M-dwarf, and nearly every M-dwarf likely has at least one super-Earth, and these worlds are close enough, on cosmic scales, to reach with current instruments. Not physically, no technology exists that could carry a probe to even the nearest of them in any reasonable time, but in terms of the light they cast across the void, in terms of the data that can be extracted from that light, with patient observation, they are within reach. A transit spectrum can reveal the composition of an atmosphere. A planet crossing its star with a thin veil of atmosphere absorbs some of the starlight passing through that atmospheric layer, and the specific wavelengths absorbed carry the chemical fingerprints of the gases present. From dozens of light years away, with a large enough telescope and enough transits, the chemistry of another world's sky can be read. This is not routine, it is difficult and slow, and requires instruments of a precision that only recently became achievable. But it has been done for some worlds, and it is being done for more. The super-Earths that are close enough and large enough and orbit quiet enough stars are already being observed with exactly this intent. Their atmospheres, if they have them, are being read. But this is the observational picture, and the deeper physical story runs beneath it like bedrock. The galaxy, in its statistical heart, is a place where small rocky worlds of 1 to 10 Earth masses form readily and commonly and persist for billions of years in close orbits around their host stars. The solar system, which taught us what a planetary system was, happens to lack this class entirely. The gap in our own family of worlds, the missing mass range between Mars and Jupiter, is not a gap that appears anywhere else with the same consistency. It is our particular arrangement, our specific outcome, and while it produced a world on which intelligence developed and built radio telescopes and launched space observatories and read the light from distant planets, in that respect, it is clearly not without interest. It is not the common outcome. The common outcome is a super Earth, a rocky world between 1 and 10 times Earth's mass, orbiting its host star in weeks or months, bearing down on its surface the weight of a sky heavier than our own, shaped by formation processes that left our solar system's middle range empty. This is the usual planet. This is the expected outcome. And the Sun, moving through its slow arc around the galactic center every 220 million years or so, passes through neighborhoods where this kind of world is everywhere, packed into tight orbital systems around red dwarfs, present around yellow stars like itself, present around orange stars, present in the habitable zones of some of them, present in baking close orbits of others, present in the cold distances of some, present in the warmth of a few. The 8 planets of the solar system, their familiar order, their well-studied surfaces and atmospheres and moons, represent an arrangement that is in some ways unusual. 4 small rocky worlds, then a gap, then 4 giants. The super-Earth range, 1 to 10 Earth masses, sits in the gap. It sits there empty. There is no world in that mass range in the entire solar system, not even a small one, not even an asteroid with enough mass to qualify. The gap is clean. Everywhere else it is full. Every red dwarf in the Milky Way, and there are tens of billions of them, quiet and ancient and scattered through every corner of the galaxy, almost certainly orbits at least one super-Earth. This is not a tentative conclusion, not a possibility that awaits confirmation. The statistical evidence, accumulated across thousands of detected planets and hundreds of carefully analyzed planetary systems, is consistent in its direction. Nearly every M-dwarf star hosts at least one world in this size range. The specific worlds vary. Some are hot and airless, some may be ocean-covered, some may have thick atmospheres, some may have none at all. But the mass range they occupy is the same, and the frequency with which they appear is high enough that their absence from our solar system, once recognized, seems quietly strange. The galaxy does not share our arrangement. The galaxy has its own preference, and that preference is for worlds that are heavier than Earth, but lighter than Neptune, formed from rock and iron, and sometimes deep stores of water, orbiting in the warmth of their host stars, at distances that our fastest spacecraft could not cross in 1,000 lifetimes. They are the common worlds. They are what planets tend to be, and in the dark between the stars, in every direction, they continue in their orbits, unhurried, uncounted, and vast in their numbers, long after any particular naming or noticing of them has ceased. A young star sits at the center of everything, still in its first million years. Around it, a flat disk of gas and dust spreads outward for billions of miles, glowing faintly at the inner edge where the star's heat reaches it, fading to cold darkness at the rim. The disk is nearly silent in any sense that reaches across the vacuum, but it is not still. Microscopic grains of silicate and iron and carbon drift through it in slow looping paths, tracing the faint pull of the star and the subtler pull of the gas around them. Each grain is smaller than a human hair. There are trillions of them, and they are already moving toward each other. This is where worlds begin. Not in a single event, not in a moment, but in the long, unhurried accumulation of small things touching and sticking and slowly becoming something larger than themselves. When two grains of dust collide at low speed in the quiet of the disk, they do not shatter. The forces between their surfaces, electrical, weak, patient, hold them together. One grain becomes two, two become a small cluster, tumbling gently through the gas. That cluster meets another cluster, and the process continues, so slowly that millions of years might pass before anything one could reasonably call a rock has formed. The interior of a young stellar disk holds this kind of quiet industry everywhere at once, everywhere around the star, every collision either joining or ending with a small drift of separated fragments that will eventually collide again. The disk is patient in a way that no living thing can fully be. What emerges from the first phase of this slow accumulation are bodies a few centimeters across, rounded, loosely held together, porous as pumice. The disk produces them in enormous numbers, and something happens to them then that makes world building possible at speeds the early picture of planetary formation could not easily explain. These centimeter-sized bodies do not simply drift. They feel the gas of the disk moving around them, and because the gas orbits the star at a slightly different speed than a solid particle at the same distance would, the pebbles experience a continuous headwind. That headwind costs them energy. They spiral inward, slowly at first, then faster, drifting toward the star on time scales of thousands of years, rather than the millions of years a larger body would take to move the same distance. And as they drift inward, they pass through the orbits of any growing rocky body in their path. That body, already larger and moving more slowly relative to the pebble flow, sweeps them up. A growing planetary core in the inner disk catches these drifting pebbles the way a wide, flat surface catches rain. Each pebble is small, but there are enough of them, arriving steadily enough that the core grows quickly. This is what scientists now call pebble accretion, and it changes the timescale of world building entirely. Where older models suggested that building a large rocky planet through the random collision of similarly sized bodies might take tens of millions of years, long enough for the disk's gas to have already dispersed. Pebble accretion can build a body to several times Earth's mass within only a few million years. The disk is still full of gas when the core reaches that size. What happens because of that fact shapes the entire character of the finished world. A core of several Earth masses, sitting inside a disk still rich with hydrogen and helium, begins to pull that gas onto itself. Gravity has grown strong enough. The hydrogen does not flood in all at once. It settles slowly over the core in a growing envelope, held loosely at first, thickening over time as the core's mass increases. If the disk disperses before the envelope grows heavy enough to collapse inward and trigger runaway gas accretion, the planet keeps only this modest hydrogen shell. If the disk lasts long enough and the core grows massive enough, that collapse happens, and the world becomes something else entirely, a gas giant, thousands of times more massive. Most of the bodies that reach super-Earth mass seem to stop before that threshold. They arrive at their final sizes with modest atmospheres of captured hydrogen and helium, held against a rocky surface by gravity that is several times Earth's pull. Whether they keep that atmosphere is another question, and a later one. The growing core does not stay where it formed. This is the detail that reorders everything else. The quiet event that determines where a finished planet will orbit for the rest of its life. A body large enough to feel the gravitational structure of the disk around it, but not yet massive enough to open a gap in the disk's gas, experiences a net inward force. The gas ahead of the planet in its orbit is slightly denser than the gas behind it, because the planet's gravity pulls material toward itself from both sides, but the disk's own pressure gradient creates an asymmetry. The result is a gravitational torque, a sustained directional push that slowly transfers angular momentum from the planet to the outer disk. The planet loses energy. Its orbit tightens. It moves inward. This process, called Type 1 migration, happens on timescales of roughly 100,000 years. In the life of a planetary system, that is very fast. A rocky body that forms at a distance of several times Earth's distance from its star can migrate all the way to a close, warm orbit in a fraction of the disk's lifetime, arriving near its star while the disk is still thick around it. Many of the super-Earths found orbiting at only a fraction of the distance between Earth and the Sun, close enough that their years last only days, may have traveled to those positions from much farther out, carried inward on a slow, invisible current of gravitational torque, while the disk that drove them still existed. Migration does not always deliver a single planet to a close orbit in isolation. The disk contains many growing bodies at once, each one migrating at its own rate, each one responding to the gravitational influence of the others. Bodies that reach similar masses migrate at similar speeds. When one catches another from the outside, their mutual gravity locks them together in a pattern, an orbital resonance, in which one planet completes a certain number of orbits in exactly the time the other completes a different whole number. 2 to 1, 3 to 2, 4 to 3. Locked in these simple ratios, they migrate inward together, a chain of worlds moving toward their star in a slow gravitationally bound rhythm that holds them apart even as they travel together. Some of the compact planetary systems found by space telescopes, 3, 4, 5 planets, orbiting close to the same star within distances shorter than the distance from the Sun to Mercury, may be the preserved endings of exactly this process. A chain of embryos that migrated inward together and stopped when the disk dispersed, locked in resonance and orbiting their star in the tight, orderly pattern the disk left them in. The disk shaped them, and then the disk was gone, and they remained. The snow line changes everything that falls beyond it. At a certain distance from a young star, the temperature in the disk drops enough that water vapor can no longer remain a gas. It condenses. Water ice forms directly onto the surfaces of dust grains beyond this boundary, coating them in a layer of frost and making them stickier, heavier, and more abundant as building material than the dry rock and metal grains of the inner disk. The location of this boundary, the snow line, shifts outward as the star brightens over its first few million years. But in the early disk of a sun-like star, it sits at roughly 2 to 3 times Earth's distance from the star. Inside it, the disk material is predominantly silicate and iron. Outside it, icy grains add significantly to the total mass available for planet building. A body assembling itself beyond the snow line incorporates water not as a thin surface layer, but as a substantial fraction of its total mass. Water ice is abundant enough in the outer disk that a growing planet there might end up with interior water fractions of 10, 20, or even 30% of its total mass, 10 times the water fraction of Earth, or perhaps 100 times. That water does not stay frozen. As the planet grows and its interior heats through accretion and the decay of radioactive elements, the ice melts. What forms inside is not a world with rivers and shallow seas, but something far stranger, a planet with a global ocean that begins at the surface and extends downward for hundreds, perhaps thousands of kilometers before reaching a layer of high-pressure ice, too dense to melt, and beneath that, the rocky mantle, sealed away from the water above it by chemistry and pressure alike. When such a world migrates inward, following the same gravitational current that carries its closer formed neighbors, it arrives at a warm, close orbit carrying that deep interior of water within a rocky shell. From the outside, it might look like any other rocky planet of similar size. Its surface, if it has one exposed to the atmosphere, might show water or bare rock depending on what its early history did to its outer layers. But inside, the memory of the snow line persists. The water that condensed onto dust grains in the cold outer disk, that was swept up by a growing embryo, that melted under the heat of accumulation and sank and pooled, is still there, compressed and rearranged by pressure, but present in quantities that no world that formed inside the snow line would ever hold. This is what the snow line gives to the planets that form beyond it, and what they carry with them when the disk drives them inward. They arrive changed by a boundary they can no longer see, shaped by a frost line that existed for only a few million years in the outer disk of a star that has since grown warm and steady. The journey erased the conditions that made them. The interior holds the record. It is worth pausing in the disk itself for a moment, in the long middle of the process, where the energy is not in the dramatic collisions, but in the quiet arithmetic of accumulation. A planetary embryo, the mass of a small moon, sits in the middle of the disk at a distance of, say, 4 times Earth's distance from the star. It has been there for roughly 2 million years. Dust grains and pebbles drift past it in the gentle headwind of the gas, and many of them fall onto its surface. Each impact is small, a few centimeters of rock striking a body thousands of kilometers across. The energy released is not dramatic in any single event, but the body is growing. Each day it is imperceptibly more massive than the day before. Each added gram of mass pulls the next pebble in from a slightly greater distance, widens the effective target just a little, makes the next impact slightly more likely. Growth feeds itself. Mass accumulates mass, slowly, over millions of years, in the dark interior of a disk that will one day be gone. There is a particular quality to that kind of time. It is not the explosive time of supernovae, or the sudden time of collisions. It is the time of accumulation, of one thing added to another, so gradually that no individual addition would be visible from outside. The grain settles onto the core. The core grows by that grain. The next grain follows. Nothing about any single event announces that a planet is being born, and yet across millions of years, a planet is being born. The disk holds this process everywhere at once, in hundreds of locations around the star, each one at its own pace, each one interrupted and redirected by the gravitational influence of everything else around it. Some of those growing bodies will collide with each other. When two embryos of roughly comparable mass meet, the encounter is not like any collision at the scale of human experience. At the masses involved, gravity dominates over material strength. The bodies do not simply break apart or bounce. They are pulled toward each other over the final hours of approach, accelerating under their mutual gravity, and when they meet, the impact is titanic in its scale and strangely slow in its character. Molten rock sprays outward in a slow arc. The two interiors briefly merge, the boundary between them blurring under the heat and pressure of the impact, and the combined mass begins reshaping itself under its own gravity into a sphere. The debris that was flung outward either escapes, falls back, or gathers itself into a smaller companion, a moon, or a ring of material that will eventually accumulate into a moon. The merged body is hotter than either of its predecessors. Unpacat. Energy has nowhere to go quickly in the vacuum of space. The New World's surface is molten, and it will remain molten for a long time, not thousands of years, but millions of years, cooling slowly, the heat locked beneath the dark, radiating surface, while the interior stays liquid. This is the magma ocean phase, and for super Earths, it is not a brief interlude between formation and geology. It is itself a phase of geology, one of the most important, during which the planet's composition sorts itself by density. Iron sinks toward the center, forming a core. Lighter silicates rise. The elements that do not fit neatly into either iron or silicate crystal structures, the ones that will later be important for life, for volcanism, for the long story of the planet's chemistry, migrate according to their own preferences through the slow convection of the molten rock. The larger the body, the longer the magma ocean persists. A planet several times Earth's mass holds more heat from the impact that formed it, loses that heat more slowly relative to its volume, because the ratio of surface area to interior volume is smaller and carries a larger inventory of radioactive elements whose decay adds heat steadily from within. The first solid crust on such a world does not form at the surface all at once. It forms at the cooler edges, where the planet curves away from its own radiated heat, where thin patches of darker rock solidify over the orange glow, and are then broken up by convection from below and remelted over and over until the cooling is deep enough and steady enough to hold. What happens in the disk to a growing embryo in the period just before it reaches its final mass depends partly on timing and partly on location, and the two are linked in ways that took decades of observation and modeling to begin to untangle. An embryo that reaches a mass of roughly 10 times Earth's early enough, while the disk still contains abundant hydrogen gas, can begin drawing that gas onto itself before the disk disperses. The gas does not collapse all at once. It settles in a thin envelope over the rocky surface, held against the planet by gravity, cooling slowly by radiating heat from the top of the envelope outward into the disk. The rate at which the envelope cools determines how quickly it can contract and allow more gas to flow in. For a super-Earth mass body, the envelope cools slowly enough that the process never reaches the runaway stage required to build a gas giant. What accumulates is a modest hydrogen-helium shell, thin relative to the planet's mass, but thick enough to register in observations, thick enough to matter for what the planet's surface and atmosphere will eventually be. Whether that envelope survives to the present day depends on the star. Young stars are not the placid, steady energy sources they become in middle age. In their first few 100 million years, they radiate intense ultraviolet and X-ray light, far more energetic than the visible light that carries most of a mature star's output. This high-energy radiation reaches the top of any atmosphere in a close orbit and heats it. The hydrogen and helium at the top of the envelope, heated enough, move fast enough to escape the planet's gravity entirely. They drift away into space. The escape is not sudden. It is a slow tide, a continuous atmospheric erosion that removes the outer layers of the captured gas over millions of years. For a super-Earth in a close orbit, this stripping can remove the entire hydrogen envelope within a few 100 million years of the star's most active phase. What remains is the rocky core, massive enough to retain heavier gases, water vapor, carbon dioxide, nitrogen, but stripped of the light envelope that was its first atmosphere. The planet that emerges from that process is chemically and physically very different from the planet that existed before. It is denser, smaller in radius, darker, and bare in a way that the hydrogen-wrapped version was not. This is the signature of the radius gap, that narrow band of scarcity in the population of known planets between roughly 1.5 and 2 times Earth's radius. Below that gap sit the stripped rocky cores, the super-Earths proper. Above it sit the worlds that retained their hydrogen envelopes, the mini Neptunes. The gap between them is not a random feature. It is the mark of photoevaporation, written into the statistics of thousands of planets, the stellar stripping that removed the envelopes from the smaller bodies and left only the dense rock beneath. The disk assembled them together. The star sorted them apart. There is a second process, quieter and longer, that may contribute to this same sorting. The heat buried in a planet's rocky core during its formation, the energy of every impact, every pebble, every collision that built it, does not disappear instantly. It radiates outward from the core into the base of the hydrogen envelope, and that heat diffusing upward through the gas over hundreds of millions of years can do its own slow work on the outer atmosphere. This is called core-powered mass loss, and it operates on a different time scale and through a different mechanism than the stellar stripping from above, but it pushes in the same direction, toward smaller radii, toward stripped surfaces, toward the rocky outcome below the gap. The disk itself, for all its importance in building planets, does not last long. The gas component, the hydrogen and helium that make up the vast majority of the disk's mass, disperses within roughly 3 to 10 million years of the star's formation, driven away by the growing stellar radiation and by the pressure of the stellar wind. The solid component, the dust and pebbles and growing bodies, remains, but without the gas, type 1 migration stops. The gravitational torque that drove embryos inward disappears when there is no gas to create the asymmetric pressure that drove it. Wherever a planet is when the gas goes, that is where it will stay, give or take the slower dynamical reshuffling of subsequent gravitational interactions. The disk's disappearance is like a tide going out. The features it carved, the orbital resonances, the inward migrations, the ice fractions locked in the interiors of outer disk bodies, remain after it is gone. The disk built the architecture and then receded, leaving the planets to orbit in the pattern it had arranged them in, carrying the chemical signatures it had given them. For a super-Earth that formed quickly through pebble accretion, migrated inward through type 1 motion, locked itself in resonance with a neighbor, and arrived at a close orbit while still wrapped in a modest hydrogen envelope, the disk's end is also the end of the most eventful period of its existence. What follows is billions of years of relative stability. The star strips the hydrogen away, slowly or quickly depending on how close and how active the star is. The rocky surface is revealed, the interior cools partially, the radioactive elements decay. A secondary atmosphere may eventually accumulate from volcanic outgassing, from the slow release of gases held in the rock, but that is a slower and quieter story, played out over geological time. The disk had its own arc, its own beginning and long middle and end. It began as a flat, dim band of dust around a point of light, too bright to look at directly. It filled with drifting pebbles and growing embryos, and the slow gravitational dance of bodies finding their places. It drove those bodies inward, locked them together in resonance, deposited them at close warm orbits around the star it surrounded. It gave some of them water from beyond the frost line, and gave others dry rock from inside it. And then it dispersed, the gas bleeding away into space over a few million years, the structure that had organized everything fading without announcement, leaving only the planets behind. A planet that formed in the outer disk beyond the snow line has migrated inward now and stopped. It orbits close to its star in a period of only a few days. Its surface, if there is a surface, is warm. Its interior holds water in quantities that no world in our own solar system contains, and the rocky mantle presses down on a layer of water that the pressure and temperature may or may not allow to be liquid, depending on the mass and the heat flow and the chemistry of the outer layers. Below the mantle, an iron core sorted out during the long ago magma ocean phase rotates in its slow warm darkness. Nothing about the view from outside this world announces what it carries. It is a point of dimming in a light curve, a slight periodic wobble in its star's spectral lines. It has a radius and a mass and an orbital period, and from those numbers one can infer a density, and from the density one can begin to guess at composition. Whether the density requires water or pure rock or some mixture, that calculation sits at the edge of what current observations can resolve. The water could be there, it could be abundant. A world shaped by the snow line, carried here by a disk that is long gone, still holds the record of where it was born, somewhere in the ratios of its interior layers. The disk assembled it from dust and distance. The migration brought it close. The star's radiation worked on its outer layers. What remains is a rocky world, massive and dense, orbiting in the warm inner zone of its system, with a history written in its chemistry and its bulk, a history that reaches back through millions of years of accumulation and motion to the first grains that stuck together in the quiet interior of a disk that formed before the planet did, that existed before the planet existed, that built the planet and then vanished into the stellar wind. And somewhere in that world's interior, in the compressed and restructured layers that no instrument has yet reached, water that began as frost on a grain of dust in the cold outer disk still sits quietly in the dark, changed by pressure and heat and time, but present, carried all the way from the snow line to a close warm orbit around a middle-aged star, on a journey the planet itself has no memory of taking. The air presses down from above. That is the first thing. Not wind, not warmth, not the particular color of a sky, just the weight of the atmosphere itself, settling onto every surface with a force that has no equivalent in any place a person has ever breathed. On a super Earth where gravity runs 2 or 2.5 times what it does here, the air does not simply rest above the ground. It is compressed into it, forced down into a density that thickens the lower atmosphere into something almost visible, a layering of pressure that turns the sky near the surface into a kind of deep sea equivalent in the open air. The surface gravity on a world like this might be somewhere between 1.5 and 3 times Earth's, a range that sounds modest until the weight of a column of air above a single square foot of ground is calculated and found to be not the 14 or so pounds per square inch that presses on every surface on Earth, but something 2 or 3 times that before a single additional molecule of gas has been added to the sky at all. Gravity alone does not fill a sky, but pressure does something to whatever is already there. A super Earth with twice Earth's gravity and the same atmospheric mass per unit of surface area would have that gas compressed into a denser, shallower column, the same amount of air fitting into a layer perhaps half as deep, the molecules pressed closer together, the pressure at the surface climbing before any extraordinary chemistry has had a chance to contribute. Add a thicker atmosphere built up by billions of years of volcanic outgassing from a larger interior with more raw material and more heat, and the numbers begin to move into ranges that no instrument on Earth has ever measured from the inside, only inferred from the behaviors of distant light. A rocky world slightly more massive than Earth does not keep the atmosphere it is born with. The first envelope of gas a planet acquires comes from the disk of hydrogen and helium that surrounds the young star in the first few million years after formation. That gas is light, diffuse, and held only loosely by a world that has not yet reached the gravity needed to grip it through the long exposure to radiation that follows. Extreme ultraviolet light from a young star, energetic and constant, arrives at the upper atmosphere of a close planet like a slow tide. It does not arrive with force or noise. It arrives as radiation, and the hydrogen atoms high in the thermosphere absorb it and gain enough energy to reach escape velocity and drift upward into space, one by one, in a process so gradual it would take millions of years to see any visible change. The atmosphere peels away from the top. It does not evaporate quickly, it thins, the way a fog thins over a field in the morning, losing density from above, while the surface far below stays as warm and pressurized as it was before. Over millions and then hundreds of millions of years, this thinning removes the original hydrogen envelope from smaller rocky worlds entirely. The world is left bare of that first gas, or very nearly so. What happens next depends on what the planet is made of and what its interior is still doing. Beneath the surface of a geologically active super-Earth, the mantle is not still. It never was still. From the moment the planet gathered enough mass for the interior to differentiate, iron sinking toward the center, lighter rock rising toward the surface, there has been heat. Radioactive elements scattered through the rock give off energy as they decay, uranium shedding particles, thorium releasing heat into the surrounding mantle, potassium-40 contributing its portion. A super-Earth carries more of all of this than Earth does, simply because it is larger and assembled more material. The interior of a world 3 or 4 times Earth's mass holds a proportionally larger inventory of heat-generating elements, distributed through a deeper and wider mantle, and the heat they produce over geological time is considerable. That heat has to go somewhere. It moves by convection, slow-rolling cells of hot rock rising toward the base of the crust, and cool rock sinking back down, a circulation so deliberate that a full turn takes hundreds of millions of years. Where the convecting mantle presses against the base of the crust, it finds paths of weakness, fissures, rifts, conduits that open under the accumulated pressure of heat and rising material. And through these openings, gas escapes. Not the hydrogen of the original envelope that is long gone, but the gases locked in the rock itself since the planet formed. Carbon dioxide, water vapor, sulfur dioxide, nitrogen, small quantities of methane. These are the gases of the interior, the volatile compounds that formed part of the original planetary material and were incorporated into the mantle rather than remaining in the early atmosphere. Now, heated by the interior and carried upward in rising melts, they are released. A single volcanic eruption releases a quantity of gas that seems large from the ground, but is, in terms of atmospheric building, almost nothing. Over a year, a decade, even a century, the contribution of volcanoes to an atmosphere is nearly invisible. But over 1,000,000 years, over 100 million years, over 1 billion years, the cumulative release becomes substantial. The atmosphere of a geologically active super-Earth is not built in any sudden way. It is built the way sediment builds on a seabed, invisibly, patiently, one thin layer at a time, the total depth accumulating only over spans of time that exceed the time since complex life first appeared on Earth by factors of 10 or 20. Carbon dioxide accumulates particularly well. It is a heavy molecule, not easily stripped away by the same photoevaporation that removed the lighter hydrogen. It does not escape into space at the rate that hydrogen does. It sits, and it builds. In the absence of a mechanism to remove it, the reaction of carbon dioxide with exposed silicate rock that slowly converts it to carbonate minerals and locks it into stone, or the subduction of carbonate-bearing seafloor into the deep mantle, where carbon is returned to the interior and eventually re-released. Carbon dioxide simply accumulates. On a planet with active volcanism, but no process for removing gas from the sky on a planetary scale, the pressure at the surface rises, slowly, over geologic time. A thick carbon dioxide atmosphere is not merely a chemical change, it is a change in the physical conditions at the surface that compounds itself. Carbon dioxide absorbs infrared radiation, the heat that a warm surface radiates upward after absorbing light from the star. Instead of passing through the atmosphere and escaping to space, that radiated heat is absorbed by the carbon dioxide and re-radiated in all directions, including downward, back toward the surface. The surface warms. A warmer surface radiates more heat upward. More heat is trapped. The surface warms further. The carbon dioxide that was formerly dissolved in any liquid water or locked in near-surface rocks begins to be released into the atmosphere at a higher rate. Pressure builds again. Temperature climbs again. The cycle is not fast. Nothing atmospheric on a planetary scale is fast, but it is consistent and it is self-reinforcing in ways that eventually carry the surface state, far from anything a human frame of reference would recognize as ordinary. Water vapor participates in this cycle as well. On a world where water exists, and many super-Earths may have formed with water incorporated into their rock or delivered during the early period of bombardment, the warming of the surface causes more water to evaporate. Water vapor is itself a greenhouse gas. It traps heat. As temperatures rise, the atmosphere holds more water vapor, more heat is trapped. The surface grows warmer still. This is not a spiral without end. Eventually, a new equilibrium is reached, as it always is. But that equilibrium may rest at surface temperatures far above the boiling point of water at ordinary pressures. Except that on a high-pressure super-Earth, water does not boil at the temperatures it boils at on Earth. Pressure suppresses the boiling point. At a pressure of 10 times what Earth's atmosphere exerts at sea level, water boils at a temperature of roughly 300 degrees Fahrenheit, higher than it does at the surface here. At 100 times Earth's atmospheric pressure, it boils at a temperature higher still. In the most extreme scenarios considered for high-mass super-Earths with thick secondary atmospheres, surface pressures might reach hundreds of times what presses on the Earth's surface, conditions comparable to what exists not in Earth's open air, but in Earth's ocean, at depths of several miles. At such pressures, liquid water can persist at temperatures that would flash it instantly to steam in the open air of any familiar environment. The ocean surface is calm. The sky above is opaque with cloud, thick with water vapor and carbon dioxide, dark at the lower altitudes with the density of the compressed air. Above the cloud deck, out of sight from the surface, the star shines on. Its light reaches the top of the atmosphere and is partially reflected back to space by the thick, bright clouds. What gets through descends into the haze and is absorbed before it ever reaches the ground. The surface of such a world is perpetually dim, not from the absence of a star, but from the depth of the atmosphere above it. A similar dimness exists at the bottom of a deep ocean, not full darkness, but a filtered, diffuse, pressure-heavy quiet. Light arrives at the surface in scattered, weakened form, reddened and softened by the long passage through dense air. The warmth at the surface is not the warmth of direct starlight. It is the residual warmth of an atmosphere that has trapped heat for millions of years, and holds it with the patient completeness of a closed room. Not every super Earth arrives at this state. The final atmospheric condition of a rocky world depends on many factors that vary from system to system, from planet to planet, and across geological time. A world at a greater distance from its star receives less radiation. A world around a quieter, older star experiences less extreme ultraviolet bombardment in its youth and may retain a more moderate atmosphere. A world with an efficient mechanism for removing carbon dioxide from its sky, perhaps through vigorous silicate weathering across exposed rock surfaces, or through some form of geological cycling that returns carbon to the mantle, might hold its atmosphere in a steady state, far cooler and more hospitable. The range of outcomes from the same basic starting materials is wide, and the same planetary mass can produce atmospheric states that have almost nothing in common, depending on which way the variables tilted in the early billions of years of a particular world's history. Two planets could be held side by side, matched in mass and age, orbiting stars of the same temperature at the same distance, and one might bake dry under a carbon dioxide sky, while the other was stripped of its atmosphere early and now shows bare rock to a cold, clear vacuum. The difference might come down to how active the interior remained, how vigorous the volcanic outgassing was relative to the rate of atmospheric loss, how much water was present in the early material. The outcomes diverge from such small initial differences. Both planets are super-Earths. The worlds they became are nothing alike. Before a super-Earth has any persistent atmosphere at all, before the interior has had time to outgas in any sustained way, before the original hydrogen envelope has finished escaping, there is an earlier state that a newly formed world passes through on its way to whatever it eventually becomes. It is not a quiet state. A planet assembling itself from smaller bodies in the first tens of millions of years after a stellar system forms, does so violently in a series of collisions so energetic that the energy they release is sufficient to melt rock on a global scale. The final large impacts in this process, a body the size of a small moon striking a growing planetary core at several miles per second, release energy so completely into the planet's interior that the entire outer layer of the world is melted. Not just the surface, not just a deep region, the entire rocky shell, down to the boundary with the iron core, becomes liquid, the magma ocean. It is the name for this state, and it is plain and accurate. Rock melted throughout, covering a sphere. The color of a cooling lava flow is familiar, that dull glow orange of barely molten basalt, but the scale here is not a flow or a volcanic plain, it is a world. Every surface feature that will eventually characterize the planet, every ridge, every crater rim, every volcanic plateau, is still in the future. For now, there is only the slow, viscous movement of molten rock at global scale, and the heat of a magma ocean is not merely the heat of molten stone, though that alone is considerable. It is the accumulated kinetic energy of every collision that built the planet, absorbed into the rock and converted to warmth that now has nowhere to go quickly. The surface of the magma ocean radiates heat to space. The crust of the star radiates heat to the planet. But the interior holds its heat for far longer than the surface loses it, and the time required for the outer layers of a super-Earth to cool from fully molten to partially solid can stretch from tens of millions to hundreds of millions of years. The larger the planet, the more material to cool, the more energetic the accretion history, the more heat delivered to the interior. A super-Earth of 4 or 5 times Earth's mass, formed in an environment where the final impactors were large and the accretion was late and energetic, might maintain a global magma ocean for a period longer than the span from the formation of Earth to the present day. During this time, the planet is not static, even in its molten state. The surface of the magma ocean is not uniform. Where the star's light strikes most directly, the surface is hottest. Where heat radiates most efficiently to space, patches of thin, dark crust begin to form at the edges, rafts of cooled material that thicken slightly before being overturned by the convecting liquid beneath and remelted. The first solid rock on a young super-Earth is not a continent. It is a thin skin, dark and fragile, forming and dissolving at the margins of a still glowing ocean. It forms in silence, or as close to silence as a planet comes. There is no wind yet, no ocean, no rain, only the slow surface of molten rock absorbing light and radiating heat, and at the very edges, in the cooler regions, the faint beginning of something solid. The atmosphere above the magma ocean is not empty. The heat of the surface drives intense outgassing. Water vapor, carbon dioxide, and other volatiles that were trapped in the colliding bodies and released by the heat of accretion fill the sky above the molten surface in a thick, high-pressure cloud. This atmosphere is not breathable in any sense. It is superheated vapor at enormous pressure, more like the interior of a boiler than anything recognizable as a sky. But it is the first substantial planetary atmosphere, forming from the same process that will build the long-term secondary atmosphere in the geological future. What is different is the temperature. At magma ocean temperatures, the chemistry of this early atmosphere is determined not by biology or mild geological processes, but by the thermodynamic equilibrium of gases in contact with molten rock. A different chemistry entirely from what comes later, when the surface has cooled and the planet's outgassing becomes the slow, steady work of a deep interior rather than the frantic release of a world still liquid to its outer layers. As the surface cools over millions of years, the crust thickens. The dark rafts of solid rock spread inward from the margins, growing thicker and more stable as the rate of convective overturning decreases with the decrease in temperature. At some point, the rafts coalesce. The ocean of magma is no longer fully open to the sky. Islands of crust join into a broken, uneven surface, and the remaining magma is confined below in isolated pockets, and then, over further millions of years, in the deep interior alone, the surface is still hot by any ordinary measure. Rock that has just solidified from a melt is warm for a long time, but the temperature is no longer above the melting point of silicate minerals, and so the crust holds, the first solid surface of a super-Earth. It is not flat. The convection that drove the mantle beneath it has left structures, elevated regions where rising material pressed upward before the crust solidified over it, lower basins where cooler material descended. These features are not like the mountains or plains of a mature planet with a long geological history. They are the raw imprint of convective cells, preserved in newly solid rock, waiting to be reshaped by the geological processes that will follow across the billions of years ahead. The surface is dark, basaltic rock, heavy with iron and magnesium, does not reflect much light. It absorbs what the star sends, and gradually, over the long geological future, the interior of the planet will continue to process it, heating it from below, fracturing it, flooding portions of it with fresh volcanic material, wearing it with whatever atmospheric processes the sky above provides. The sky above the newly solid surface is still thick. The water vapor that built up during the magma ocean phase does not vanish when the surface cools. Some of it precipitates. On a super-Earth, that has cooled enough for liquid water to be stable at the surface, and whether this happens at all depends on how far the planet is from its star and what the pressure and composition of the atmosphere allow that water vapor condenses and falls. The rain on a world like this is not the gentle rain of a temperate afternoon. At the temperatures and pressures of a world still losing heat from its magma ocean phase, any rain that falls is hot, falling through a high pressure atmosphere onto a surface that is only recently solid. The chemistry of the rainfall dissolves the surface rock slowly. The minerals released by that dissolution enter whatever bodies of liquid water form at the surface, and the water chemistry begins to evolve away from pure precipitation towards something more complex, something that carries the signature of the rock it has been running through. This is not life. It is far earlier than life. It is the planet establishing its first chemical budget, learning, in the language of slow geological equilibrium, what it has to work with and how the basic materials will be distributed across the surface and subsurface as time continues. A super-Earth with a different composition of starting materials, or a different orbital distance from its star, or a different mass that produces a different surface gravity and therefore different atmospheric behavior, arrives at this first solid state through the same sequence of events, but with very different initial conditions. And the first solid state is not the end of the story. It is the beginning of the long geological story, the first page of something that will continue for billions of years, the interior cooling, the surface changing, the atmosphere accumulating or thinning, depending on the balance of forces that act on it from within and without. What a super-Earth sky looks like when it has had billions of years to settle into whatever equilibrium its particular circumstances allow is a question whose answers vary. There is no single answer. A world at the outer edge of its star's habitable zone, with a modest secondary atmosphere of nitrogen and carbon dioxide, might have a sky that is clear and thin above a cold, bare surface. A world close in, with a thick atmosphere built by sustained volcanism and held in by high surface gravity, might have a sky visible from the surface only as a crushing opaque weight of hot gas. A world that retained just enough water and just the right atmospheric composition might have a sky that is cloudy in the way Earth's sky is cloudy. A sky that moves, that holds weather, that cycles water between surface and atmosphere in patterns not entirely unlike the patterns of any familiar afternoon. The pressure at the base of a thick atmosphere on a high-mass super-Earth is not something any earthly experience quite prepares a sense for. On Earth, the atmosphere presses on every surface at the equivalent of what a column of water roughly 33 feet deep would press, a weight that is real, but that no human body notices in daily life, because the body is pressurized to match it. At surface pressures 100 times higher, the analogy is to a column of water more than 3,000 feet deep. That is not a pressure humans have experienced at the surface of a world. Pressure at that level compresses gases into denser forms, forces molecules closer together, changes the way heat moves through the air, changes the way sound travels, changes the conditions under which chemistry occurs. The air at the base of such an atmosphere is not simply heavier air. It is a different material in thermodynamic terms, denser, more opaque, more chemically reactive in some ways, more stable in others. The sky above this compressed layer graduates as altitude increases. Near the surface, the atmosphere is dense and dark with its own mass. Higher up, as pressure decreases with altitude, the layers become thinner, cooler, more transparent. Near the top of the atmosphere, where the air is thinning toward the threshold of space, Photochemistry begins. The same ultraviolet radiation that would strip lighter elements from the planet if they were present instead drives chemical reactions among the heavier molecules that remain, creating secondary chemical species that would not exist in the surface chemistry. The chemistry of a thick super-Earth atmosphere is not a single chemistry. It is a stack of different chemical environments, each determined by the pressure and temperature at its altitude, each different from the layers above and below. The surface, beneath all of this, is held in conditions that the atmosphere determines. On a world where surface pressure and temperature remain within a certain range, not too hot, not too cold, not too pressurized for liquid water, the surface is where chemistry can accumulate, where minerals can react slowly with water over geologic time, where the slow exchange between rock and atmosphere and liquid that characterizes a geologically active world can proceed. On a world where conditions are more extreme, where temperatures push past the stability of liquid water even at high pressure, or where the surface pressure is high enough that the chemistry of the rock and the overlying atmosphere is governed by conditions more like those in an industrial furnace than those in a terrestrial environment. The surface is a very different kind of place. There is a world in our own solar system that offers a partial analog to one version of this story. Venus, at slightly smaller than Earth's mass, has a surface pressure 90 times Earth's and a surface temperature of roughly 860 degrees Fahrenheit, hot enough to melt lead, produced by a thick carbon dioxide atmosphere that has trapped heat for what appears to be billions of years. The super-Earth versions of this story are scaled up in mass, in gravity, and in the potential thickness of the atmosphere, but the mechanism is the same one that Venus demonstrates in our own neighborhood. Carbon dioxide accumulates. The greenhouse effect traps heat. The surface temperature climbs, and the process becomes self-sustaining. On a planet with greater mass and therefore greater gravity, holding a deeper column of gas in place, the conditions that Venus represents can be imagined extended, intensified, taken further in the direction the physics points. But Venus is one outcome. It is the outcome of a world that lost its water, that had no efficient mechanism for sequestering carbon dioxide, that passed through a runaway greenhouse phase and did not emerge from it. A super-Earth at a somewhat greater distance from a somewhat cooler star with a somewhat smaller initial carbon dioxide inventory might arrive at a very different equilibrium. The range of outcomes is wide because the inputs are numerous, and the timescales over which they interact are long enough for small differences to compound into large divergences. This is what makes super-Earths difficult to characterize from a distance, and what makes each one that comes under study a distinct world, not an instance of a type, but a particular history frozen at the moment of observation. Two super-Earths of identical mass, orbiting at the same distance from identical stars. One has a thick carbon dioxide sky, a surface temperature above the boiling point of water, even at the elevated pressures that reign at its surface, and no liquid water anywhere on its face. The other has been stripped of almost all its atmosphere by the activity of its young star, and now rotates in bare silence, the rock exposed directly to space. No gas buffering the temperature swings between the side that faces the star and the side that turns away. The first is hot and pressurized, and alive with chemical activity in the atmospheric layers above its surface. The second is cold and bare, and still. Both are super-Earths. Neither has anything that would look familiar from the ground. The diversity of these outcomes sits quietly inside the statistics. When the data from planet surveys are examined, super-Earths appear around the majority of the stars in the galaxy. Most of those worlds have surfaces and skies that no one has seen, conditions that exist only as numbers derived from transit depths and radial velocity measurements and the careful interpretation of planetary structure models. The specific state of any particular surface, whether it is bare rock or liquid ocean or baked desert or crushed beneath 100 atmospheres of carbon dioxide, is mostly unknown. What is known is the mass range, roughly, and the orbital period, and from these the density in the best cases, and from density an estimate of composition. The sky remains hidden behind a transit spectrum that requires more time and more careful observation to read than most individual worlds have yet received. The weight of the atmosphere presses on whatever surface is there. It does not stop pressing. On a geologically active world, the volcanism that built the sky continues adding to it, increment by increment, eruption by eruption, over spans of time that exceed anything easy to hold in mind. The interior cools, but slowly. On a super Earth with a large inventory of radioactive elements and a thick mantle, the heat that drives the volcanism persists for longer than it would on a smaller world. The outgassing continues. The atmosphere continues to build. The surface continues to be shaped by the interaction between the gas above it and the rock beneath it, and the heat that moves through it from inside. A magma ocean slowly solidifying over tens of millions of years draws the first dark crust forward from the edges of its still molten surface. The crust forms in patches. It dissolves. It reforms. At the margins of the still liquid regions, thin sheets of dark basaltic rock harden and hold, briefly, then longer, then in spans of time that begin to accumulate into something stable. The glow of the molten interior is visible through the fractures in the early crust, orange light seeping upward through the cracks in newly formed rock, cooling as it rises, solidifying a little further with each passing 1,000 years. The outer surface of the planet dims. The glow retreats inward. The rock that covers the surface grows thicker and darker, absorbing the light of the star above and radiating heat more slowly than the open magma beneath it did. The planet's first solid surface emerges not all at once, but in the way that ice forms on a slowly cooling pond, from the edges across the still surface, until the last open patch of liquid closes over and the world above and the world below are separated by stone, and then the stone holds and the long geological story begins, and the heat that remains inside the world continues its slow outward journey through the rock, through the convecting mantle, through the fissures and vents that carry volcanic material and gas upward toward the sky, one eruption at a time, one thin increment of atmosphere added to what came before, the sky thickening almost imperceptibly over millions of years, while the surface cools and hardens and waits in the dark, and the starlight for whatever the interior still has to give. Around a small red star, 49 light years from the sun, a rocky world moves through its orbit in the dark. It takes less than 25 days to complete one full circuit. The star it circles is so dim that this close orbit still places the planet inside a band of space where liquid water might rest on stone, where temperatures might neither scorch everything away nor freeze it permanently still. That band, the habitable zone, is the first thing any astronomer asks about when a new world is found, and it is the question this particular world has answered, at least in part, just by being where it is. The habitable zone is not a place, it is a condition. It is the range of distances from a star where a rocky planet, given enough atmosphere, could sustain liquid water on its surface without that water boiling away into the sky or locking permanently into ice. Around a star like the Sun, this zone falls between roughly 90 million and 150 million miles out, a broad, temperate ring. Earth sits near its inner edge. Around a small red star, the equivalent zone pulls in dramatically, and it falls between roughly 9 and 37 million miles from the star. A planet in that zone completes its year in days. It orbits in a space the Sun's habitable zone would dwarf many times over, and yet the physics of warmth and light make it equivalent, the right amount of energy arriving at the surface, the right conditions for water to exist in its liquid form if the rest of the world cooperates. These red stars, the small, cool, numerous ones called M dwarfs, outnumber every other type of star in the Milky Way. For every star like the Sun, there are perhaps 3 or 4 of them, faint and long-lived, burning slowly through hydrogen at temperatures low enough to keep them going for 100 billion years or more. Planets are common around them. Super-Earths are especially common around them. And so the question of whether worlds in the habitable zone around M dwarfs can actually support life is not an idle question at all. It is the most numerically relevant question in the search for life anywhere beyond Earth, because there are simply so many of these systems, so many planets in approximately the right position, and the answer determines whether most of the galaxy's potentially habitable real estate is truly habitable or merely close. A planet in a tight orbit around a red star does not move the way Earth moves. It does not spin freely, presenting each face to the star in turn, cycling through day and night in a familiar rhythm. Gravity has had time to slow it down. In the close orbits of M-dwarf habitable zones, over long enough timescales, the same gravitational tidal forces that lock Earth's moon to always show the same face toward Earth do the same thing to a planet. One side faces the star forever, the other faces permanently away into space. The line between them, the terminator, runs in an endless circle around the planet, neither day nor night, a belt of permanent twilight where the star hangs fixed and low on the horizon. On the day side of such a world, the star does not rise or set. It simply stays, hour after hour and year after year, heating the surface in a single persistent pool of warmth. The rock beneath that star absorbs heat until it reaches equilibrium. The air above it, warmed from below, rises and spreads outward toward the edges. On the night side, no light arrives at all. The surface cools until it reaches equilibrium of a different kind, the deep cold of space, unbroken by any sun. Carbon dioxide can freeze directly from the atmosphere onto the dark surface there. Water ice accumulates and does not melt, and between these extremes, the terminator persists. A ring of wind and transition, where the rushing air from the hot side meets the cold, pooling down from the dark, where the sky above might be permanently clouded and the temperature neither as brutal as either extreme. Whether life could find purchase in such a world depends entirely on what happens to that moving air. If the atmosphere is thick enough, circulation does the work a spinning world cannot. Warm air rising from the day side carries heat poleward and toward the terminator, spreading warmth from its source, delivering it into the dark. Climate models built over the past decade suggest this circulation can be powerful enough to keep liquid water near the point directly beneath the star, and along the terminator itself, where temperatures settle into a temperate range, neither too hot nor too cold. A planet that cannot rotate can still be habitable if its atmosphere is dense enough and well mixed enough to ferry warmth from the lit side to the dark. The belt of twilight along the terminator is where the most temperate conditions might persist. Winds there carry air from both directions, the warm outflow of the day side and the cold drainage from the night. In the models, the Terminator is neither the hottest nor the coldest place on such a world. It is the middle ground, and on a world of extremes, the middle ground is where something like stability lives. A river there would flow neither toward permanent day nor permanent night. It would simply run through the half-dark, under a sun fixed at the edge of the sky, and the water in it would stay liquid because the air above it kept the temperature in a range that water tolerates. Whether that temperate band extends far enough, whether it persists against the slow drift of climate towards some more extreme state, whether the star allows it, these are questions that models approach but cannot fully settle. The star itself is not a passive source of gentle warmth. M-dwarf stars, especially younger ones, produce intense bursts of X-ray and ultraviolet radiation. Flares erupt from their surfaces far more frequently than solar flares erupt from the sun. A planet orbiting this close is hit by these bursts regularly, and over millions of years, the cumulative effect of that radiation on an atmosphere can be severe. Ultraviolet light breaks apart molecules in an upper atmosphere. It splits water vapor into hydrogen and oxygen. The hydrogen, light enough to escape, drifts away into space. The oxygen may react with surface minerals and vanish, or it may accumulate, or it may be lost itself in time. Repeated flares push harder against the tenuous outer layers of an atmosphere, accelerating the erosion around a young M-dwarf in the billions of years before the star settles into its calmer middle age. A planet in the habitable zone might lose substantial fractions of whatever initial atmosphere it began with, stripped away by stellar activity during the very period when the planet was young, and perhaps building the chemical conditions for something living to begin. This does not mean M-dwarf habitable zones are hostile to life with certainty. It means the picture is more layered than a simple estimate of distance allows. A planet that formed with a large initial water inventory might lose a great deal of it and still retain enough. A planet with active volcanism replenishing its atmosphere through geological outgassing might sustain what stellar radiation removes. The net outcome depends on a balance between supply and loss, and that balance is different for every world, at every star, across every history of formation and migration. The models suggest that habitable conditions are possible around M-dwarfs. Whether they are common, whether they arise wherever the position is right, or only under particular combinations of circumstance, that is an open question that the galaxy holds quietly without announcing its answer. Beneath the surface of a massive super-Earth orbiting within a habitable zone, a different kind of challenge to life assembles itself in the dark. On Earth, the ocean floor is stone. Where water meets rock, minerals dissolve and reform. Carbon moves from the water into the rock and back again. Volcanic vents on the ocean floor exhale chemicals that rise into the water column and become food for organisms that have never seen sunlight. This contact between ocean and rock is not incidental to life on Earth. It is woven through everything: the recycling of elements, the regulation of chemistry, the provision of the raw materials that living things use to build themselves. On a super-Earth, several times Earth's mass, the ocean above a rocky seafloor is deeper by an enormous margin. Not deeper the way the Pacific is deeper than the Atlantic, but deeper by orders of magnitude, an ocean that descends not miles but hundreds of miles, thousands of miles, pressing down with the weight of all that water, all that mass, all that distance from the sky above. And deep enough, water does something unexpected. It freezes, not because it is cold enough for ordinary ice, but because the pressure becomes so great that even at temperatures above what would normally be required, water locks into a dense crystalline structure called high-pressure ice. There are several such forms. Ice 6, Ice 7, each a product of extreme compression, each denser than liquid water, each settling on the seafloor of a deep enough ocean, like a solid layer of stone. This layer of high-pressure ice at the bottom of a deep ocean world sits between the liquid water above and the rocky mantle below. That barrier is not trivial. On Earth, the mineral exchange between ocean and rock is continuous and essential. Chemicals leach from rock into water. Water carries them to living things. The rock is renewed by volcanism and changed by contact with the sea. On a world where high-pressure ice seals the ocean floor from the rock beneath, that exchange slows enormously or stops. The ocean chemistry drifts. Whatever minerals were in the water when the ice formed stay in the water. Whatever the rock below might offer stays in the rock. The carbon cycle, the phosphorus cycle, the slow geological metabolism that on Earth has kept the chemistry of the ocean in a range where life can persist. These processes are interrupted by a floor of ice that no ordinary ocean current can cross. Whether this matters for life depends on what life is doing and where it began. If life on such a world arose at volcanic vents on a rocky seafloor, and then the ocean deepened over geological time until high-pressure ice sealed the vents away, the life above the ice layer might continue on what resources remain in the water column. Or it might not. The question is not one that Earth's biology can answer from experience. It is a condition that has no analog in the place where biology is known to exist. And the honest response to it is that it raises a real concern about whether deep ocean worlds can sustain the kind of mineral cycling that seems to matter for long-term life, while acknowledging that the universe may have found solutions that have not yet been imagined. The surfaces and skies of super-Earths in the habitable zone remain largely hypothetical in terms of direct observation. What can be measured, what telescopes can actually read from 40 or 100 light years away, is the light that passes through the thin atmospheric ring at a planet's edge as it crosses the face of its star. Transmission spectroscopy is the name of the technique, and it works like this. As a planet crosses its star, a small amount of starlight passes through the outer layers of the planet's atmosphere, rather than being blocked by the solid disk of the planet itself. Different molecules in that atmosphere absorb different wavelengths. Water vapor absorbs at some wavelengths. Carbon dioxide absorbs at others. Methane, ozone, each have their own signatures. The light that reaches a telescope after passing through the atmosphere is missing those wavelengths, tiny subtractions from the spectrum, faint but measurable fingerprints of the chemistry overhead. The signal is small. For a planet the size of a super-Earth transiting an M-dwarf star, the atmosphere represents a fraction of a percent of the total light being blocked. Detecting the atmospheric signal within that tiny fraction requires a telescope of significant sensitivity, a star that is not itself too active and noisy, and many transits observed over time, stacked and averaged until the signal rises above the noise. The James Webb Space Telescope is the first instrument capable of attempting this for rocky super-Earths around nearby M-dwarfs. Its mirror, 6.5 meters across, gathers enough light to detect the kinds of atmospheric signals that previous telescopes could only theorize about in these planet classes. The first attempts have brought caution. Early observations of some nearby super-Earths have produced flat spectra, no atmospheric features detected at all, which could mean no atmosphere exists, or that the atmosphere is too thin or too uniform in composition to leave a readable mark, or that high-altitude clouds have blanketed the spectrum in a featureless gray. A flat spectrum is not a failure of observation so much as a result that genuinely constrains the possibilities. Knowing that a world probably lacks a thick hydrogen envelope is information. It means the planet is denser and rockier than a world swathed in hydrogen gas, and it opens the question of what, if anything, a secondary atmosphere outgassed from the interior might look like. A thinner, heavier collection of gases dominated by carbon dioxide, or nitrogen, or water vapor, the kind of atmosphere built slowly from below. The biosignature that draws the most careful attention from the people who think about these things is oxygen. On Earth, oxygen is produced in vast quantities by photosynthetic organisms, plants, algae, cyanobacteria, that split water molecules using sunlight and release the oxygen as a byproduct. Oxygen is reactive. Left to itself, it bonds readily with iron in surface rocks, with volcanic gases rising from the interior, with organic molecules in the soil. Without constant replenishment, atmospheric oxygen on Earth would drop dramatically within a few million years. The oxygen now present in the atmosphere is there because living organisms keep putting it back. If a telescope detected significant oxygen or its derivative ozone in the atmosphere of a rocky planet, the most straightforward interpretation would be that something is producing it continuously, something in the simplest scenario alive. The caution around this interpretation is genuine and important. There are abiotic pathways to atmospheric oxygen, processes that produce it without life. The photodissociation of water vapor in a planet's upper atmosphere, followed by the escape of hydrogen into space, leaves oxygen behind. A planet that began with a large water inventory and lost a significant fraction of it to stellar radiation might accumulate a substantial oxygen atmosphere from this process alone, without any photosynthesis, without any biology at all. Distinguishing a biosignature from an abiotic mimic requires seeing not just the oxygen, but the context, whether carbon monoxide is present alongside it, whether the ratios of different gases make sense for a living world or for a planet undergoing slow atmospheric erosion. Life leaves a consistent chemical disequilibrium. Different molecules coexist that would not coexist on a purely geological world. Methane and oxygen together, for instance, would react and destroy each other in geologically short time, so their simultaneous presence in an atmosphere requires something continuously producing both, and on Earth, the organism that produces methane and the organism that produces oxygen are as different as life gets, yet both exist at once, maintained by biological productivity against the chemistry that would otherwise erase them. No biosignature has been detected in any super-Earth atmosphere. No claim of atmospheric chemistry has been confirmed on a rocky world in a habitable zone. The observations are young, the instruments are new, and the nearest candidates are dozens of light years away. The science exists now at the edge of what can be measured, feeling along that edge carefully, and the results so far say only what is not yet confirmed, which is itself a genuine thing to say. Among the worlds that have drawn the most patient and sustained attention is a super-Earth called LHS 1140b. Its star is a quiet M dwarf, quiet meaning it produces fewer flares and less violent stellar activity than many of its class, which matters for any atmosphere trying to persist on a close-in planet. The planet has a mass roughly 5.5 times Earth's. It orbits inside the habitable zone. Its density, inferred from the combination of its size and its gravitational tug on the star, suggests it is a rocky world rather than a gas-dominated one. Whether it holds an atmosphere and what that atmosphere contains are questions still being read slowly from the light it intercepts and returns. Observations from the James Webb Space Telescope have begun to narrow the possibilities. A flat spectrum would rule out a thick hydrogen-dominated atmosphere. A feature in the spectrum might suggest something heavier, carbon dioxide perhaps, or water vapor, or nothing at all that current models anticipated. The world is 49 light-years away. The light arriving from that direction set out before many living people were born. It carries, encoded in its wavelengths, the partial truth of a world that has been orbiting its star for billions of years without anyone reading it until now. There is a kind of patience required by this science that has no analog in most human experience. The question of whether LHS 1140b holds an ocean or a thin atmosphere or nothing at all above bare rock cannot be answered by going there. It can only be answered by looking very carefully at very faint signals across a very long distance, over many observations, over many years, building a picture molecule by molecule from the absorption lines in a spectrum. The people who do this work do not expect fast answers. They build instruments to last decades. They plan observation programs that will run through the careers of researchers not yet in graduate school. The question is large enough to deserve that patience, and the method has no shortcut. What would it mean to find oxygen and ozone in the atmosphere of LHS 1140b, or methane alongside carbon dioxide in chemical proportions that make no sense without something generating and regenerating them? The honest answer is that it would mean a great deal while still falling short of certainty. A single detection of a potentially biological signal would be scrutinized from every direction. Alternative abiotic explanations would be constructed and tested. Follow-up observations would be planned for wavelengths that might distinguish between interpretations. The scientific community would proceed with a care proportional to the magnitude of the claim, which is very large. Because the claim that chemistry exists on another world consistent with the presence of living organisms is perhaps the most consequential thing anyone has ever had the possibility of saying. The tidally locked super-Earth hangs in space with one face held permanently toward its small red star. On the bright side, the surface is warm. On the dark side, the surface is cold. Between them, the terminator runs its endless ring, a line of perpetual twilight where wind moves and the sky carries the mixed light of a sun fixed forever at the horizon. Below, if the planet is warm enough and wet enough and geologically active enough, water might rest on stone, minerals might dissolve, chemistry might cycle, and in that chemistry, in some arrangement that no observation has yet confirmed and no telescope has yet resolved, something might be doing what chemistry alone does not do: building, maintaining, reproducing, persisting against the slow dissolution that time and physics press against all organized things. The distance between that possibility and a confirmed answer is filled with instruments and patience and light. The light is already traveling. The instruments are open to it. The patience is long, and the question will not hurry. Around red dwarf stars, smaller and dimmer than the sun, in orbits that complete themselves in weeks, on worlds several times Earth's mass, the conditions for liquid water exist in a form that has no close parallel here. The habitable zone of a red dwarf is a ring drawn close to the star, 9 to 37 million miles out, a range that the distance from Earth to the Sun contains with room to spare. A planet in that ring orbits in days. It is close enough to feel the tidal pull that locks its face to the star, close enough to absorb the stellar flares that roll outward in bursts of radiation over the billions of years of a red dwarf's slow, persistent life. Whether the atmospheres of worlds in these tight orbits survive the long bombardment of stellar radiation is a question without a single answer. It depends on how much atmosphere the planet began with, on how geologically active it remains, on whether the star's activity faded over time into something less erosive, on whether the planet's own magnetic field, if it has one, deflects some of what the star sends. Magnetic fields arise from the churning of conducting material deep inside a planet, which requires a molten core maintaining convection over geological time. Whether super-Earths retain such convection for long enough, under the pressures and heat flows their large interiors generate, is a problem the models approach with differing answers depending on assumptions about composition and cooling rate. A planet with a strong magnetic field is better protected from the stellar wind, the constant outflow of charged particles that flows from any star and pushes against the outer atmosphere of any orbiting world. On Earth, the magnetic field deflects most of the solar wind around the planet rather than into the upper atmosphere. Without it, the stripping of atmospheric gases by charged particles would be faster and more severe. Whether the super-Earths of M-dwarf habitable zones tend to have strong magnetic fields, whether their large iron cores stay liquid long enough and convect vigorously enough to generate and sustain them, these are connected to questions about interior pressure and heat flow that cannot yet be answered from observation alone. The interior of a world that is 5 or 6 or 8 times Earth's mass is a place that physics has theories about and that no instrument has directly measured. And yet the logic of statistics is persistent. If super-Earths are the most common planet type in the galaxy, and M-dwarfs are the most common stellar type, and the habitable zones of M-dwarfs are close enough that their super-Earths can be detected and characterized with present technology, then the super-Earths of M-dwarfs are the best available window onto whether rocky worlds in habitable zones can sustain the conditions life requires. Not because they are the most Earth-like, they may be very different from Earth, but because they are the nearest, the most numerous, and the most accessible to the instruments that can read their light. The atmosphere of a rocky planet in a habitable zone, breathed across the distance between its star and any telescope pointed toward it, contains the first layer of the answer. The chemical composition tells something. The presence or absence of water vapor tells something. The presence of oxygen or its absence, the presence of methane, the balance of gases that chemistry alone would not sustain. Each adds a layer to a picture that is being assembled slowly, observation by observation, transit by transit, year by year. A single transit of LHS 1140 Ball across its star dims the starlight by a small fraction for a few hours. In that brief passage, a fraction of the star's light passes through the atmosphere rather than being blocked by the solid planet. The wavelengths that arrive at the telescope carry the subtraction of whatever the atmosphere absorbs. Each observation adds a little more signal. Each year brings more transits, more data, more constraint on what the atmosphere can and cannot be. The picture does not arrive all at once. It assembles itself slowly in the gap between what is known and what has not yet been measured, in the patient accumulation of photons that left a distant star and arrived at a mirror and became something a person could eventually read. 49 light-years is not far by the measure of the galaxy. It is far enough that the light arriving from that direction is old, 49 years old at minimum, older for the star's own ancient light, underneath the planetary signal. But it is close enough that a telescope built for this purpose can see something real in the spectrum. It is close enough that the question of LHS 1140b's atmospheric state is a question the current generation of instruments can at least begin to answer, even if the final answer takes decades more. The planet moves silently in its orbit, 24 or 25 days to circle once around its dim red star. It has done this for billions of years. It does not know it is being watched. It does not know that 49 light years away, a species of organisms on a slightly smaller rocky world has built instruments and pointed them at the star it circles and is reading, very carefully, the light that its transit slightly and briefly changes. The planet simply moves. The star simply glows. The light simply travels, carrying its information patiently across the dark between. On the terminator of that distant world, where the permanent day meets the permanent night, wind moves through whatever air exists there. If the air is thick enough, the wind carries warmth from the bright side and distributes it into the dark. If the surface holds water, the water holds warmth too, redistributing it through currents that no tide raises, no moon pulls. The temperature at the terminator in the best available models settles into a range where ice can melt and where liquid water can persist at the surface without boiling away. That range is not guaranteed. It depends on exactly how much atmosphere remains, exactly what that atmosphere contains, exactly how much heat the star provides, and how much the planet retains. The uncertainties are real. They are held openly, without distress, as the edge of what is known, a boundary that moves with each new observation, each new model, each new transit of the planet across its star. The boundary is not the end of the question. It is just where knowledge stops for now, and the rest continues quietly beyond it, in the dark and the light, and the wind of a world that is moving through its orbit at this moment, as it has for billions of years, and will continue to for billions more, whether or not the answer ever arrives here. The habitable zone of a red dwarf is a narrow band drawn close to a dim star, and inside it, super-Earths move in short, tight orbits, their day side held forever toward the warmth, and their night side facing the long dark of space. The question of what lives in those atmospheres, or whether anything does, is among the deepest questions the current instruments were built to approach. The answer has not arrived. The light carrying it is still traveling. The telescopes are waiting for the next transit, and the one after that, and the one after that. Each pass a few more hours of signal, a few more photons contributing to a picture that grows slowly clearer in the careful, unhurried accumulation of what the universe allows to be seen. LHS 1140b traces its quiet path through the dark. Its star glows dull and red against the background of older, fainter stars. The light from that system reaches every direction, including toward a small yellow star 49 light years away, around which a world is orbiting that has started to ask questions about it. The asking is patient. The answer is slow. The planet continues its circuit regardless, steady in the gravity of its star, carrying whatever it carries, rock, air, water, silence, or something else entirely, around and around in the long, unhurried dark. Below the crust, the rock gives way. It does so slowly, over kilometers, the familiar gray stone of a surface dissolving into something darker and denser, pressed by weight into forms no surface light has ever touched. The temperature climbs, the pressure climbs, and the minerals that built the upper layers begin, one by one, to become something else, the same atoms rearranged by force into configurations tighter and heavier than the forms they held above. This is what the interior of a super-Earth is like. Not a deeper version of what the surface holds, but a place where familiar matter has been quietly transformed into something with no name in ordinary experience, shaped entirely by the mass above it, pressing down. Descend far enough, and even the concept of rock becomes uncertain. On Earth, the transition from crust to mantle happens roughly 20 miles beneath the surface, where temperature and pressure together shift the character of the rock from rigid to something that flows too slowly to watch, but flowing nonetheless over millions of years in vast and quiet convective currents that carry heat upward from the deep. The upper mantle holds a mineral called olivine, pale green and glassy, the most abundant mineral in the planet by volume. It is found in some meteorites. It washes up on certain beaches in small pale grains. It is, in one sense, ordinary, but olivine does not stay olivine. Deeper down, where the weight of everything above reaches 100,000 times the pressure of the air at Earth's surface, olivine changes. Its crystal structure collapses inward. The atoms, still the same atoms, silicon, magnesium, oxygen, shift into tighter bonds, into a new arrangement called wadsleyite, denser and darker and differently behaved. Deeper still, under greater weight, wadsleyite gives way to ringwoodite, and then to post-perovskite, each transition marking a pressure threshold that reshaped the very geometry of the mineral's interior. These transitions happen on Earth at well-mapped depths. Their signatures appear in seismic data. They are among the things geologists can say with confidence about the world underfoot. On a super-Earth, those same transitions happen, but they happen far shallower. The weight of a larger world pressing down means that olivine, if it exists at all in such a planet's upper layers, reaches its first transformation sooner, with less depth needed to accumulate the necessary pressure. And the transitions that mark Earth's deepest mantle, the ones that require pressures near the core boundary, occur partway through a super-Earth's mantle. What comes after those? What mineral phases exist in the deepest layers of a world 5 or 8 times Earth's mass is something that no laboratory has yet been able to replicate in full, because generating those pressures in a controlled setting at any useful scale remains beyond current tools. The diamond anvil cell sits on a laboratory bench and holds a flake of mineral no wider than a human hair, pressed between the tips of 2 gem-quality diamonds by forces that can reach millions of atmospheres across that tiny area. It is, in its way, a quiet machine. It makes no noise. Under a microscope, the mineral inside it shifts color, shifts transparency, sometimes cracks and reforms. The pressure inside is extreme beyond ordinary comparison, and still, for the deepest layers of the most massive super-Earths, even this instrument does not reach far enough. Those interior regions remain, for now, a matter of calculation. Pressures inferred from equations of state, mineral phases predicted from theory, the behavior of iron and silicate extrapolated far beyond the range of anything measured directly. Iron at the center of a super-Earth is a strange thing to contemplate. At Earth's core, iron is already under immense pressure, compressed into a dense inner solid, surrounded by a liquid outer layer, and the pressures there already exceed what most surface intuition can make sense of. In a super-Earth of 4 or 5 Earth masses, the pressure at the core boundary may reach 10 times that, or more. The iron at that depth is not the iron of a nail, or a bridge, or a meteorite resting on a table. Its crystalline structure has been rearranged by force into a denser configuration, and the exact nature of that configuration, how its atoms are ordered, how it conducts heat, how it behaves as the planet slowly cools, is something researchers have only recently begun to access. Using shock compression experiments that send high-powered lasers into thin foils of metal for a fraction of a second, generating conditions that last too briefly to study easily, but long enough to leave a measurable trace. The core of a super-Earth is, in this sense, genuinely unknown terrain, not hypothetical, not invented, real, existing, right now, inside every one of the billions of super-Earths distributed across the galaxy, and entirely beyond the reach of any instrument that has ever been built, or any instrument that could plausibly exist, because there is no way to visit such a core, no way to drill to it, no way to send a signal through tens of thousands of kilometers of solid and semi-solid planetary matter and receive a coherent answer. What is known comes from physics and chemistry at the edges of the currently achievable. What lies in the gap between those edges and the true center of such a world is a kind of structured uncertainty, known to be there, known to follow physical law, and still only partially describable. Below the surface of a super-Earth, heat moves. It moves in the same way it moves through Earth's mantle, not by conduction alone, but by convection, by the slow overturning of material that is warm at depth and cool above, rising and sinking in vast currents that carry heat outward over hundreds of millions of years. On Earth, this convection is what ultimately drives plate tectonics, the great slow cracking of the surface into plates that drift and subduct and collide, recycling rock back into the mantle at ocean trenches and building mountains where plates press together. It is one of the things that, by the current best understanding, contributes to Earth's long-term climate stability by burying carbon dioxide that accumulates in the atmosphere back into the deep rock where it cannot trap heat. Whether a super-Earth can do the same is one of the genuinely open questions in planetary science. The forces that drive plate tectonics on Earth are well studied. Oceanic crust, denser than continental crust, eventually becomes heavy enough to sink back into the mantle at subduction zones, a process called subduction, and the motion of the sinking slab is part of what pulls the whole plate along. The question for super-Earths is whether higher gravity helps or hinders this process. Higher gravity increases the driving force that pulls dense rock downward, which should encourage subduction. At the same time, higher gravity increases the pressure inside the lithosphere, the rigid outer shell of the planet, in ways that may strengthen it against the bending needed to initiate a subduction zone. The lithosphere of a super-Earth, under its greater weight, may resist folding more than Earth's does. The two effects push against each other, and current models do not fully agree on which wins. What some models suggest is that many super-Earths may settle into what is called a stagnant lid, a single unbroken shell of rigid rock covering the entire planet, neither cracking into plates nor subducting anywhere. Mars is in this state now. Venus may be as well, or something close to it. A stagnant lid is not a geologically dead planet. The mantle can still convect beneath it. Volcanism can still reach the surface through cracks and hotspot plumes, but the organized planet-wide cycling of material that characterizes Earth's plate tectonics does not occur. The surface holds. The interior churns in silence beneath it. For a stagnant lid super-Earth, the consequences for climate may be large. On Earth, carbon dioxide released by volcanoes eventually makes its way back into the mantle through a chain of steps. It dissolves into rain, reacts with silicate rock in a process called weathering, and the resulting carbonate minerals wash into the ocean, where they eventually become part of ocean sediment, and the ocean sediment eventually subducts at trenches, carrying the carbon back into the mantle, where the heat and pressure break it apart, and it returns to the atmosphere through the same volcanoes that released it to begin with. This cycle, the carbonate-silicate cycle, acts as a slow thermostat. When carbon dioxide concentrations in the atmosphere rise, temperatures rise, rain becomes slightly more acidic, weathering accelerates, and more carbon dioxide is drawn down. When concentrations fall, weathering slows, and volcanic release tips the balance back. Over tens of millions of years, the cycle keeps Earth's climate within a range where liquid water can exist on the surface most of the time. A super-Earth without plate tectonics has no subduction. Carbon enters the atmosphere through volcanoes. Rain falls and weathering begins. But the carbonate minerals that form have nowhere to go underground and no mechanism to return the carbon to the mantle. The carbon accumulates. Slowly, over millions of years, a stagnant lid super-Earth may build toward a thick carbon dioxide atmosphere with no natural mechanism to draw it back down, pressing toward greenhouse conditions without a thermostat in place to moderate the climb. This is not a certainty. There may be other carbon sinks on such a world, carbon dissolved in oceans or trapped in surface rock by processes that do not require subduction. The full range of planetary behavior is likely wide. Some super-Earths may find stability through mechanisms that Earth does not use. Others may not, because the honest answer is that the diversity of geological fates among the billions of super-Earths in the galaxy is probably broader than any current model can contain, because the models are built on the one example that is fully accessible, which is Earth, and Earth may be only one path among many. Heat is the thread that runs through all of it. Every rocky planet begins warm. The energy of its formation, the kinetic energy of every collision that built it, converted to heat, is locked into its interior from the moment the last large impactor struck and the growing body first achieved something like a stable sphere. On Earth, that initial heat has been leaking outward ever since, and it still contributes to the warmth in the mantle, though it diminishes over geological time. But there is a second source of heat, one that does not diminish on the same time scale as the remnant warmth of formation, because it is produced continuously by the slow decay of radioactive atoms distributed through the rock. Uranium, thorium, and a particular isotope of potassium, these three are the primary contributors. They are present throughout Earth's mantle and crust in trace amounts, and their decay releases heat at a rate that has kept the planet geologically active for 4.5 billion years. The amount of heat they produce is not large on a human scale. A cubic meter of mantle rock radiates a tiny fraction of a watt from radioactive decay. But across the enormous volume of an entire planet's mantle, these tiny fractions sum to something significant, and they do so year after year, billion after billion years, with a half-life long enough that the process is still going, and will still be going long after the sun has evolved off the main sequence. A super-Earth has more of everything. More mass means more mantle. More mantle means a larger absolute inventory of uranium, thorium, and potassium-40, even if their concentration per unit of rock is the same as an Earth's. The total heat production inside a super-Earth of 5 Earth masses is therefore much greater than an Earth itself, not proportionally, because larger planets also have more rock to heat, and larger surfaces through which to lose warmth, but enough that the balance tips toward a planet that runs warmer and stays geologically active longer. How much longer is a question that stretches past any easy intuition. Earth's interior heat has sustained volcanism and mantle convection for roughly 4.5 billion years. A more massive super-Earth with a larger radioactive inventory and a higher interior temperature to begin with may sustain comparable geological activity for longer, possibly far longer, possibly for timescales that exceed the current age of the universe, if current models of its thermal evolution are followed forward. This is not a statement about the distant future of any particular known planet. It is a description of what the physics implies for a certain range of planetary masses, given reasonable assumptions about their composition. A world large enough and warm enough inside may still be geologically young in every functional sense when it is older than any star that currently shines. The mantle of such a world convects. The convection is slow, current speeds measured not in meters per second, but in centimeters per year, a pace that only becomes meaningful when multiplied by millions of years. Rock that is slightly warmer than its surroundings rises, barely, over vast distances and timescales. Rock that has cooled by giving up heat to the layers above it sinks equally slowly back toward the deep. The currents are not simple columns. They fold and flatten and divide, rising in broad plumes and sinking in thin sheets, driven by temperature differences of a few hundred degrees across the full depth of a mantle, thousands of kilometers thick. Where these plumes reach the surface, they produce volcanism. On Earth, hotspot volcanoes, like the ones that built the Hawaiian Islands, or the ones that created the vast flood basalts of the Deccan Plateau, mark where a plume of especially warm mantle has risen far enough to melt the base of the lithosphere and push lava through to the surface. On a stagnant lid super-Earth, this is perhaps the primary mechanism by which interior heat escapes. The surface does not recycle, does not crack into organized plates, does not carry rock into the deep-at trenches, but the mantle beneath it still rises and falls, and where the heat is concentrated enough, it still breaks through. Volcanic gases rise through those breaks. Carbon dioxide, water vapor, sulfur dioxide, nitrogen, methane in smaller amounts. These are the gases that emerge from the interior of a rocky planet through volcanism, the secondary atmosphere built slowly over geological time after whatever primary atmosphere the planet captured or retained from its formation has been lost or transformed. On a super-Earth, the scale of this outgassing depends on the scale of volcanic activity, which in turn depends on the interior heat. A volcanically active super-Earth could outgas substantially more carbon dioxide and water vapor over its history than Earth has, building a thick atmosphere over time. The thickness of that atmosphere under higher gravity produces its own effects. Gravity compresses the atmospheric column. The same mass of gas distributed across the lower atmosphere of a super-Earth occupies a smaller vertical extent than it would on a less massive planet, because the gravity pulling it down is stronger. This means that the surface pressure beneath a given atmospheric mass is higher on a more massive planet. A super-Earth that has outgassed roughly the same total inventory of carbon dioxide as Earth has water in all its oceans might sustain surface pressures that no analogy in the human world quite captures. Hundreds of times the pressure at Earth's surface, pressing down on any rock or liquid that exists there. Under that pressure, the behavior of familiar substances shifts. Water at Earth's surface boils at 212 degrees Fahrenheit. Under a pressure of 100 atmospheres, water does not boil until temperatures that would reduce steel to near softening. A super-Earth with a thick carbon dioxide atmosphere and high greenhouse warming could, in principle, sustain surface temperatures well above what is needed to boil water at Earth's pressure and yet still hold liquid water on its surface because the atmospheric pressure prevents the phase transition. The ocean on such a world would be extremely hot, extremely pressurized, and still liquid. It would bear no resemblance to the temperate blue surface of Earth's seas. Whether life could exist in such conditions is a question that remains genuinely open and is not the concern here. What matters in this moment is the physical picture, the weight and the heat and the pressure, the column of gas pressing down on a dark surface, the deep rock still warm from decay, the slow convective currents in the mantle below, the plumes of volcanic gas rising through fissures in a rigid lid that holds and holds over billions of years. The interior of a super-Earth is not a more extreme version of Earth's interior. It is a different kind of place, shaped by forces of the same type as Earth's, but operating at scales and durations that produce a qualitatively different world, one where the things that are familiar, rock, iron, heat, gas, are present but transformed. The transition zones between mantle layers are on Earth, narrow bands at specific depths where seismic waves change their speed as they cross from one mineral phase to another. Geologists mapped these boundaries using the natural seismometry of earthquakes, whose waves travel through the planet's interior and emerge on the far side, with their speeds and character changed by the materials they pass through. It is one of the quiet achievements of Earth science to know the interior of a planet without ever going there, by listening to how it vibrates after it is struck. A super-Earth cannot be listened to this way, not yet, not with any existing instrument. The only information available about its interior comes from its average density, derived from its mass and radius, and from the theoretical framework built on mineral physics and thermodynamics. The average density of a super-Earth tells something. A dense planet is more rocky. A less dense planet may hold water or gas in its interior. A very dense planet may have a proportionally larger iron core. But density alone is a single number describing an entire world, and the number of possible interiors consistent with any given density is large. Two super-Earths of identical mass and radius could have very different interiors, one with a large iron core and a thin mantle, another with a smaller core and a mantle enriched with water, another with a thick silicate mantle and a core of different composition, and all three could produce the same average density. The degeneracy of the problem, the technical word for this ambiguity, the situation in which multiple solutions fit the same data, means that interior structure cannot be determined from mass and radius alone. Additional information is needed: the atmospheric composition, the chemical environment of the host star, observations of tidal deformation as the planet orbits. None of these entirely resolves the ambiguity. Some of it may never be resolved. And yet the minerals inside those worlds are there, taking their forms under pressure right now, this moment, as the light from their host stars reaches the instruments of telescopes on Earth. The iron at their centers is compressed into whatever configuration the pressure at those depths demands. The mantle minerals are arranged into whatever phases survive at those temperatures and pressures. The volcanic gases are rising or resting. The convective currents are turning, centimeter by slow centimeter, through rock that has not been cold in billions of years and may not be cold for billions more. The deep interior of a planet is a place that operates on its own timescale. The surface of a world, any world, can change quickly in geological terms. A large impact reshapes it in hours. Volcanism can bury a plain in lava over centuries. Erosion, where atmosphere and liquid exist, reshapes coastlines and valleys over millions of years. These are fast processes by the measure of the interior. In the mantle, a single convective cycle, the full overturning of a parcel of rock from depth to surface and back again, takes hundreds of millions of years. The radioactive elements driving the heat decay, with half-lives measured in billions of years. The phase transitions in the mineral record hold their configurations for as long as the pressure and temperature conditions that created them remain stable, which in the deep interior can be essentially forever on any human timescale. There is a quality of patience in the deep rock that no surface phenomenon quite matches. On a super-Earth whose radioactive inventory is large enough, the interior is not simply old, but actively ongoing in a way that dwarfs the timescales of surface events. The mantle convects, the plumes rise, the gases emerge at the surface. All of this happening not in the past tense of a geological record, but in the continuous present of a world that has not finished forming itself, even if it has been orbiting its star for 5 billion years. Geological activity on Earth will continue for billions of years more. The interior is far from exhausted. And on a more massive super-Earth, that continuation is extended further still, pressed outward into a future so remote that the stars of the current epoch will long since have completed their lives. Post-perovskite is the mineral phase that occupies Earth's deepest mantle, just above the core boundary, where pressures and temperatures are at their extreme within the mantle's range. It was only confirmed experimentally in 2004, which is recent in the history of a science that has been studying the interior of the Earth for more than a century. The experiments required generating pressures comparable to those at Earth's core mantle boundary and reaching the temperatures that exist there and holding the sample steady enough to make a measurement. The result was a mineral phase unlike anything observed at the surface, denser, differently structured, found only in the narrow zone between the hot iron core and the cooler, convecting mantle above. In a super-Earth of several Earth masses, post-perovskite may be present not just in a thin zone, but throughout a large fraction of the mantle, because the pressures required to stabilize it are reached much shallower. Below that, in the deepest mantle of such a world, there may be mineral phases that have never been synthesized in any laboratory, phases whose existence is predicted by computational methods and thermodynamic extrapolation, but never directly observed because the tools to make them do not yet exist. These phases have no names. They are placeholders in a periodic inventory of unknown matter, waiting for the instruments and methods that will eventually perhaps make them accessible. The core of a super-Earth is largely iron, with some fraction of lighter elements dissolved into it: sulfur, oxygen, silicon, carbon in various proportions depending on the chemistry of the world's formation. The exact composition of the core affects how the core behaves, whether it crystallizes from the inside out as the planet cools, whether the crystallization drives convection in the liquid outer core, whether that convection generates a magnetic field. Earth's magnetic field is generated this way by the slow crystallization of the inner core, releasing heat and light elements that stir the liquid outer core into convective motion, and that motion combined with the planet's rotation, generating a dynamo. Whether super-Earths have magnetic fields generated by a similar mechanism is uncertain. Larger cores with higher pressures may crystallize differently. The melting point of iron at extreme pressures rises steeply, which means that a super-Earth's core may be entirely solid despite higher temperatures, depending on the balance between pressure and heat. A solid core would not convect, and without convection, the dynamo may not operate. A super-Earth without a magnetic field would be more exposed to the stellar wind, the flow of charged particles from the host star, which could gradually strip away the lighter components of its atmosphere over long periods of time. Whether this stripping is significant depends on the star's activity, the planet's orbital distance, and the atmospheric composition, and the range of outcomes is wide. Some super-Earths likely have magnetic fields, some likely do not. The ones that do may retain their secondary atmospheres more effectively. The ones that do not may slowly lose volatile gases from the top of their atmospheres over billions of years, shifting the atmospheric composition and pressure over time in ways that feed back into the surface conditions. No single model covers the full range of possibilities because the initial conditions, composition, core size, rotation rate, stellar environment vary enough that the space of outcomes is genuinely large. The crust of a super Earth, that thin outermost layer above the mantle, is the part of the planet farthest from the extreme conditions of the interior and closest in some ways to the familiar. Rock, probably basaltic in character across much of the surface, dark, fine-grained, the product of mantle melt that reached the surface through volcanic activity, or in regions that have seen multiple cycles of magmatic processing, something closer to a granite-like composition, lighter, more silica-rich, the result of repeated melting and refining of the same material. On Earth, the continents are made of rock that has been processed this way over billions of years, separated out from the denser oceanic crust by the same magmatic sorting that has been running since the planet was young. On a stagnant lid super Earth, the character of the crust depends on how long and how vigorously the volcanism has operated, and whether the products of successive volcanic cycles have been mixed back into the mantle or preserved at the surface. Without plate tectonics to destroy old crust at subduction zones, ancient volcanic rock may survive at the surface for far longer than it would on Earth, accumulating a geological record that is old and deep and largely unmodified by the burial and metamorphism that constantly reworks Earth's crust. In that sense, the surface of a stagnant lid super-Earth might hold a more intact archive of its early history than Earth's surface does, though reading that archive from a distance, with no surface mission and no samples, remains a problem with no near-term solution. The heat flowing outward from the deep interior of a super-Earth crosses all of these layers, core, mantle, crust, over timescales that extend from the formation of the planet to a future far beyond the present. The flow is not uniform. It is concentrated in plumes where the mantle is locally hot, and reduced in regions where the mantle is cooler and the convective currents are weak. At the surface, that pattern of heat flow expresses itself in the distribution of volcanic activity, clusters of vents and fissures above active plumes, quiet plains above cooler regions, the surface shaped over long time by the invisible currents below. That shaping continues, right now, on every rocky super-Earth in the galaxy, not in a way that changes quickly enough to observe across a human lifetime, or 100 human lifetimes, or a civilization's entire history, but it continues. The atoms of iron and silicate and water and carbon inside those worlds are not still. They move in the only way that stone can move, slowly, over scales of time that make the word slow feel inadequate. They carry the heat of formation and the heat of decay outward through thousands of kilometers of rock, arriving at the surface at last as warmth, too faint to feel from here, too dim to measure across the distances involved, but real. The deep rock of a super-Earth does not know it is observed. It does not know about the telescopes that measured the radius of the planet it forms, or the spectrographs that may one day read the gases at the top of its atmosphere, or the theorists who extrapolate mineral phases into pressure regimes that laboratories cannot yet reach. None of that changes what happens in the interior. The olivine transitions into its denser forms at the depths where the pressure demands it. The iron at the center holds whatever crystalline structure the extreme compression creates. The radioactive atoms in the mantle decay at the rate their nuclei dictate, releasing heat that has no choice but to move outward, slowly through the rock. This process has been running for billions of years on the worlds that hold it. It will run for billions more. On the most massive of those worlds, it will run for longer than the current universe has existed, outlasting most of the stars that presently shine, outlasting the conditions that made its formation possible, continuing in the dark long after any surface it might have known has changed beyond recognition. There is no drama in this, no urgency. The heat moves at its own pace through rock that has no preference for stillness or motion. The minerals hold their configurations for as long as the pressure holds them there. The convective currents turn in silence in the mantle, following the equations of fluid dynamics in conditions that no human-built device has ever entered and likely never will. The core, whether molten or solid or some phase with no common name, persists in the dark at the center of the planet, exactly as old as the planet itself, exactly as permanent as the forces that shaped it. Somewhere, across the distance of dozens or hundreds of light years, a super-Earth turns on its axis in the dark. Its star gives it a slow rhythmic face of light and shadow across whatever surface it holds. Below that surface, the deep rock is unchanged by the turning. The mantle has no day and no night, no concept of the star above, only the upward pull of heat and the downward pull of weight. The rock rises and falls in currents that will still be running long after the star above has finished its life, long after the surface has been changed by whatever the billions of remaining years will do to it. The interior of a world is the quietest place in the world. It does not carry sound. It does not admit light. It holds pressure so immense that the language of ordinary experience runs out of useful comparisons, and the only recourse is mathematics. And still it is made of the same matter as everything else, the same atoms that formed in stellar cores and scattered through the galaxy in old explosions, the same iron that runs through every rocky planet, every meteorite, every grain of dust in every protoplanetary disk orbiting every young star in the sky. The matter is not foreign. It is the same matter, differently arranged, under conditions that push the arrangement past anything accessible from here. And the process that holds it there, the pressure, the heat, the slow decay, the slow convection, is not special to those distant worlds. It runs in the earth underfoot. Right now, kilometers below any ground, the mantle is turning in currents of warm rock, carrying heat that was there before the first living thing drew breath. The iron at Earth's center is compressed into its own dense phase, the pressure there immense and permanent on any scale of time that human life can touch. The difference between here and those distant super-Earths is one of degree. More mass, more pressure, more heat, more time. The same processes extended into a range where they produce outcomes that Earth does not show. But the processes themselves are the same ones that built the ground below, that keep it warm, that will keep it active long after anything on the surface has changed beyond recognition.